Night rests on the Pacific like a sheet of cold glass, and a pair of watchful eyes stare upward from volcanic rock. The eyes are not human, at least not directly. They belong to a network of small telescopes that breathe on their own, yoking silicon and starlight into a patient vigilance. Their name carries a promise and a warning. Asteroid Terrestrial Impact Last Alert System, ATLAS. Most nights, the system drinks in a river of familiar noise. Known asteroids step across the field like steady patrons in a dim bar. Satellites drag straight scars through each exposure. Cosmic rays puncture frames with reckless pinpricks. The software learns to ignore what can be ignored. Then something draws breath in the noise, faint enough to be a rumor, a pale thread that refuses to sit still in the way most things do. It registers as difference, as subtraction, as what remains after the ordinary is peeled away. The pipeline flags it. A human notices because the machine tells a human to notice. The operator leans in, opens the stacked images, and feels that odd tightening that lives at the seam between curiosity and foreboding. The streak is thin. The streak is fast. The streak does not belong to any bound family that the catalogues keep. A preliminary orbit is sketched by the same mathematics that guided sailors before clocks learned to keep faith with the sky. Fit a curve to points, let gravity explain the rest. The numbers come back with a shape that is not a leash at all. Eccentricity higher than 1, velocity at infinity that refuses to be 0. The sun is not this object's home, only a lamp it will pass. Somewhere beyond the shell of frozen comets that halo the planets, somewhere between dark and darker, the something was nudged and began a journey that ends with a quick bright sigh near a yellow star, and then continues into another emptiness. The designation feels like a threshold. In 3 characters, a world of inference blooms, a third known visitor from outside the solar cradle, an arrival with habits taught by other suns, or by no sun at all. It will have a name that includes Atlas, because names are promises as well as labels, and because the system that raised the alarm deserves a line in the story. Astronomers breathe quietly through the first night. Requests ripple through networks, to confirm, to measure, to sharpen the orbit by fractions, and then by more. Somewhere in a control room, mugs of cooling coffee stand beside checklists with pencil marks. The sky moves as it always moves. A small dot moves against it, with just enough disobedience to feel like a whisper in the cathedral. What is the absolute worst that could happen? A voice asks. The kind of voice that the species cannot help but cultivate whenever risk and wonder occupy the same room. It is not a theatrical question to those who live under the nightly dome, and it is not mere dread. It is a method. Begin at the edge, map the contours of fear, then walk back toward the probable. The object is not a person. It does not intend. It does not carry malice in its nucleus. Yet the cosmos does not care about intention, only energy and momentum and the places where paths cross. Most paths do not cross. Space is vast, and planetary defense is mostly a matter of statistics and patience. Yet fear has its own mathematics. Interstellar objects can move fast. Their kinetic energy scales with the square of that speed. A modest mass becomes something else at tens of kilometers per second, something with consequences that do not fit neatly in old tables. Worst is a word that bends like light near gravity. Worst can mean a direct collision, a strike that writes a fireball into the air and a crater into the crust. Worst can also mean the subtle violence of dust and fragments, a veil that throttles sunlight a little too long, a shiver through crops and supply chains. Worst can even be the quiet chaos of rumor, markets that move because eyes moved first. He watches nothing, because he is not a he at all, but the narration imagines a watcher to fit our need for a figure at the window. This watcher follows the dot, stack by stack, frame by frame, as if each exposure is a footstep toward comprehension. The dot brightens by fractions. The motion relative to the star background changes by commas, small and then less small. The inference tightens its belt around a hyperbolic curve. A sense gathers in the room that this is not a domestic comet waking up for the 1000th time. This is a migrant with a different dialect of ice and dust. A catalogue of previous surprises hums in the background like a generator. Stories of an earlier messenger that showed no coma even while sunlight coaxed it, stories of one that did bloom and shed material like a true comet, leaving a tail that reeked of other kitchens. No two visitors teach the same lesson. The truth is that there is no stable handbook for cold bodies born elsewhere. Chemistry changes with stellar nurseries. Porosity varies with pressure histories. Spin states can be as strange as the ways stones roll on mountains when no one is watching. Between the facts sits a field of question marks. That field is fertile soil for a mind that wants to imagine the cliff edge first. In the hours after the flag, astronomers split their attention into two intertwined projects. First, a hunt for certainty, because certainty shrinks corridors of alarm. Second, a modelling of contingencies, because a civilization that ignores small probabilities learns hard lessons. The first demands more photons, more timestamps, more spectra in lines that can reveal what molecules are breathing off the surface. The second demands a staircase of what-ifs. What if outgassing grows asymmetric and kicks the trajectory sideways by a whisper? What if thermal stress cracks the body near the sun and seeds a string of boulders along the path? What if one of those boulders belongs to an orbit that happens to intersect a planet with weather and oceans and billions of thin lives leaning on electricity? In a classroom far from the mountain, a teacher pulls up a simulation on a projector. Students watch a pale dot fall toward a radiant circle, then curve and sling and depart. Someone asks if that dot can hit the planet. Someone else asks what happens if it does. The teacher answers with numbers and also with humility. The truth is that worst cases are rarely realized, yet they are essential to see. They guide preparation. They test our ability to think clearly while our animal brain is busy drawing shadows on cave walls. The simulation runs again, then again, each time with a slight tweak to a parameter that matters. On the mountain, dawn lays a thin ash of colour on the summit's cinder cones. The telescopes yield to sunlight and to daytime work lists. Data flows downhill through fibre and then across oceans of copper and glass. Somewhere in an office, a scientist opens an email with the first crude spectrum. Absorption lines whisper about volatiles. A molecule here suggests an origin story tied to a cold place. Another line hides in the noise and will need coaxing before it confesses. The shape of the continuum hints at dust that is either waking or not yet free. Nothing is final, and that is the point. The species stands at a window, looking at a guest that does not know it is a guest, and the question repeats with patient gravity. What is the absolute worst that could happen? This question does not taste like panic in the right mouths. It tastes like responsibility. Engineers imagine shields for satellites if a dusting becomes likely. Farmers ask about seasons if sunlight dims by 1% or 2. Emergency planners scan playbooks for what a meteor storm would do to skies and to nerves. Philosophers consider the fragile contract between knowledge and anxiety, and how to speak in a way that informs without unmooring. Across disciplines, a rhythm begins that feels like a rehearsal, and rehearsals are not reasons to grieve, they are reasons to breathe deeper. As night returns, the same eyes lift again. The pale thread has moved. It always moves. Now it carries with it a little more meaning, a little more weight. The orbit will be sharpened or softened by the next set of points. The risk corridor will widen or narrow. The worst case will grow teeth or lose them. The scene is exactly what it looks like. A world that learned to measure the heavens looks again, and that act of looking is both shield and song. The visitor remains a rumour etched in photons, and the rumour is enough to bind minds on several continents into quiet, deliberate attention. Somewhere, confidently, and also carefully, a person writes the line that will sit at the top of a page. 3. I. Provisional. Atlas. Pending confirmation. A name is a net, and this one will be tested by the sea it is thrown into. A small array of fast, wide eyes keeps vigil on volcanic summits and southern pampas, tuned to the faintest motions that betray a wanderer. The network carries a plain name that hides a bold mission: Asteroid Terrestrial Impact Last Alert System. Its telescopes are modest in aperture, quick in exposure, and relentless in rhythm. Each night, fields tile the sky like careful stitches. 4 passes per region to turn points into paths. Software sifts the flood, subtracts yesterday from today, peels stars away from transients, and leaves a residue of moving specks. Most specks are familiar citizens of the inner and outer belts. A few are near Earth, watched with a caution that never sleeps. Once in a very long while, a tracklet whispers of a speed and direction that do not respect any leash the sun can offer. A particular moonless interval brings such a whisper. The instrument is on a high, dry shoulder of an island mountain, where lava once ran and trade winds now steady the air. 4 exposures, separated by minutes, reveal a dim point shifting against a lattice of catalogued stars. The displacement is larger than the patterns that bind main belt objects. The trail is short, yet the rate tells a story. The pipeline flags the candidate, assigns a probability that it is not spurious, and pushes an alert to human eyes. A duty astronomer checks the stamps, blinks the frames, and makes the decision to promote the object to the world's clearinghouse for moving things, the Minor Planet Center. A provisional designation is the first badge it earns, the bland alphanumeric that says an object has arrived at the front desk. Within hours, other facilities turn their mirrors and lenses to the coordinates. Panoramic systems recover it along the predicted line, adding points that stretch the time arc. A pair of larger telescopes contribute precise astrometry, chiseling down the error bars that swell when the known path spans only a handful of hours. Each measurement feeds a solver that has served celestial mechanics since the age of Gauss. Fit a conic to the points, iterate, update residuals, test the next ellipse or hyperbola. The numbers return with a surprise that sharpens every eye at every console. The best fit wants an eccentricity above unity. The asymptote of the hyperbola points back toward a radiant that does not align with the typical inbound corridors used by comets, tied to our own distant reservoir. The barycentric speed at infinity refuses to fall to zero. Even with conservative uncertainties, the inbound energy looks too high for the object to be a domestic exile dislodged from the Oort cloud. The phrase interstellar candidate begins to travel through emails and voice channels, not as hype, but as a description earned by data. While positions accumulate, a different campaign begins. Spectroscopic attempts are organized, because ice and rock speak in wavelengths that human eyes cannot pass. A low-resolution spectrum is the first to land, recorded by a facility that can trade depth for speed. The signal-to-noise is modest, the continuum faint, yet some structure is visible. Familiar bands that announce the presence of common cometary gases do not leap out, but neither are they ruled out. The brightness suggests a size that is neither trivial nor immense, with albedo guesses adding uncertainty. These are the raw ingredients of early days, enough to sketch, not enough to paint. The calendar entry for the moment of confirmation records a time within a few sunsets of the first flag. As additional nights stretch the arc, outlying solutions collapse. The eccentricity remains stubbornly above 1. The inbound vector is compared to the local standard of rest, and analysts nod at the pattern. The speed and direction fit the population of bodies drifting between stars. The Minor Planet Center and the committees that govern names prepare a more permanent label. The third known traveller from beyond will be numbered with an I that marks a special class, and it will carry the Discoverer's network in its name. 3I, and then the survey's badge. A compact history of vigilance pressed into a brief title. The who of the discovery is never a single person. A list of names will accompany the official circular, spanning engineers who nursed cameras through heat cycles, programmers who taught code to sort the sky at speed, technicians who dusted optics, coordinators who kept one station online while another slept at dawn, and astronomers who watched the candidate long enough to elevate it. The when is a window defined by the geometry of the sky and the humility of instruments. The where is a chain of hills and observatories linked by fibre and discipline. The how is a choreography that begins with 4 short exposures and ends with a global chorus of follow-up. The network that saw it first was built for a clear purpose. It was funded and tended by people who believed that early notice matters. Each telescope offers a field wide enough to net a great many faint movers in one throw, and each is fast enough to repeat the throw until the night is a mosaic of measured motion. The sensitivity is tuned to catch city-sized bodies days before a possible approach, not to litigate the origins of ice from alien kitchens. Yet the same design that protects a planet also opens a door to a rarer prize. Interstellar objects are not looked for in a special place. They are found by systems that never stop watching. Confirmation brings a new discipline. Observers schedule time around the changing elongation and phase angle that will govern brightness. Radar specialists run numbers and admit that range and size probably put the object beyond their usual reach, though they will try if geometry is kind. Photometrists prepare to hunt for periodic flickering that could reveal a rotation state. Occultation mappers publish predictions for lucky chords where a star might blink as the object glides in front, a technique that can outline size and shape with exquisite precision if fortune and weather cooperate. Every step feeds a single question that matters to both curiosity and caution. What exactly is approaching, and how exactly will it pass? The first light curve arrives with a hint of variation. The amplitude is small but suggestive. A slow rotation seems plausible, though aliasing can fool the unwary when the cadence is thin. A few nights later, a second team reports a compatible period. The nucleus might be elongated or irregular, as small bodies often are, but nothing demands an extreme shape. These are fragile insights that will harden with time. For now, they are threads that give the mind a surface to hold. A single diagram on a shared screen becomes the center of the room. It shows the plane of Earth's orbit, the slanted cut of the newcomer's path, and the date of closest approach to the Sunday. Lines of uncertainty surround the nodes where the trajectory pierces the ecliptic. Early solutions are fat, later ones thin. The line that marks the distance to Earth at the moment of its nearest solar sweep is watched like a heartbeat. No solution allows a collision. None place the object in the narrow band where planetary tides could tear it apart by direct pull. The geometry looks clean, yet the pace of data gathering does not relax. A moving, outgassing surface can nudge itself with tiny jets. Only continued measurement can tell whether those nudges will matter. News spreads beyond the profession, as it always does when a phrase like third interstellar object appears in a headline. For the teams closest to the data, the story is simpler and more workmanlike. A small, fast point was found by a survey built to find small, fast points. The alarm was raised. The community answered. The status of the visitor shifted from rumor to verified class. Logs were written. Schedules adjusted. A new entry took its place in a short list that may grow longer as the species improves its instruments. The passage from candidate to confirmed is complete only when an official circular prints the I, the numeral, and the chosen name. That moment arrives with almost ceremonial quiet. A bulletin lists coordinates, magnitudes, velocities, and vectors. The name includes the survey because tradition and fairness require credit to flow back to the system that first saw the motion. 3. I, followed by Atlas, a compact signature that nods to the watchfulness of a species that has learned to see its surroundings as a field of moving parts. The discovery phase closes not with triumph, but with a steadying breath. The sky has offered a traveller, instruments answered. The rest of the story waits in the light that will spill from it as it curves toward the Sunday. A trajectory tells a biography in numbers. The path draws a conic, and the conic selects a birthplace. Circles and ellipses speak of loyalty to the Sunday. Parabolas trace the borderland, where a visitor could be owned by light or freed by speed. A hyperbola speaks of elsewhere. In a reference frame that uses the solar system's center of mass rather than the Sun alone, the solution requires an eccentricity above 1, a sign that the object is not bound. The orbit solver returns a hyperbolic excess velocity, the little remainder that would persist even if the Sun's gravity were turned off at infinity. That remainder is not small. Tens of kilometers per second emerge from the fit, a value that refuses assimilation into any family born within the local cold reservoirs. Geometry builds the rest. The incoming vector points toward a radiant on the celestial sphere that is displaced from the ecliptic where most domestic comets show up. The inclination rises steeply, a tilted plane that cuts the solar equator like a knife held at a deliberate angle. The argument of perihelion places the closest approach at a point that does not intersect the lanes where Jupiter rules. The longitude of the ascending node tells where the path passes through the plane of Earth's orbit. All of these elements can be measured and refined, and together they form a declaration. The object is a drifter from the deep between stars, It is not a product of the Oort cloud shaken loose by tides. It is not a captured exile that later escaped. Its memory is older than the comets bred here. The speed relative to the local standard of rest adds a note of familiarity and strangeness at once. Many small bodies roam the galaxy with velocities that match the churn of nearby stars. The vector of this newcomer resembles that pattern within expected dispersions. That resemblance is a comfort, because it suggests ordinary galactic heritage, and it is a spur, because ordinary heritage still carries extraordinary energy when folded into the sun's gravity well. A hyperbola in the solar frame is simply the echo of straight motion in a larger arena, bent by a star that is bright but small in the grand scale. Keen eyes turn from orbital elements to timing. The perihelion date can be estimated early, and with it the schedule for safe windows to study composition and rotation. The passage is swift. Interstellar objects do not loiter. They rush past like wind through a canyon. Weeks or months stand between first notice and closest approach, not the gentle years granted by distant comets that fall inward on long arcs. The short calendar multiplies the need for clarity, and it sharpens the conversation about risk. A world that wants to know the worst needs to know the map, and the map is a ribbon that weaves through the planetary plane without promising intimacy. One diagram earns special attention in every room that works with orbits. It is the plot of the minimum orbital intersection distance, the MOID, between the traveller and Earth. The MOID is not a prediction of impact. It is a measure of how narrowly two independent lanes graze. For a hyperbolic object, the MOID evolves quickly as each new night lengthens the arc of observation. Early values carry big uncertainties. Later values narrow into a verdict on proximity. The number is watched as one watches a slowly settling compass needle. A wide MOID invites curiosity and dismisses fear. A narrow MOID brings nuance, because timing must also match, and because gravitational focusing modifies straight expectations near a massive world. Gravitational focusing deserves a quiet explanation. A moving object is caressed by the pull of a planet as it passes. That pull bends the path a little. In some cases, the bending grows enough to draw a small body closer than a straight line would allow. Interstellar speeds reduce this effect compared to slower domestic meteoroids, yet they do not erase it. Calculations include this bending while they test the nearest approach. The numbers do not tremble with drama. They simply honor the physics that has shaped every meteoroid shower and every capture and every escape since the disk of planets first cooled. A second plot shares the table with the MOID. It is the phase angle through the passage, the angle between the sun, the object, and the observer. The phase governs brightness and tail geometry in the sky. Observers plan around it, but more than planning is at stake. Phase angles determine how easily a faint coma can hide within the glare of an elongate dust trail. The tail, if it grows, will point away from the sun, not along the path, so the direction of that tail relative to Earth matters for satellites and for the atmosphere. Trajectory is not only where the nucleus goes, it is also where its exhaust will point when sunlight warms volatile pockets. If volatile pockets exist, a hyperbolic path is a palimpsest of subtle influences. The planetary perturbations are present, although their signatures are faint against the large speed and the steep angle of approach. Jupiter writes the heaviest marginal note, but the geometry can spare it from the main story. Radiation pressure will whisper at dust, not rock, if dust is present. The Yarkovsky effect, the thermal push that tiny bodies feel as they re-radiate heat, is negligible for a short, hot sprint. Non-gravitational accelerations from vents, if they arise, will matter only if persistent and asymmetric. The trajectory team carries all of these into the integrator, then subtracts them again if data stubbornly prefer a cleaner, simpler path. A detail that fascinates dynamicists is the backward trace. Integrate in reverse, and the line walks out into the dark, past the heliopause, past the tide of charged particles, into the gentle gravity of the galaxy itself. Out there, the path becomes a straight line once more, at least over the modest distances that can be tested without modelling full galactic structure. That straight line intersects nothing that can be named with certainty. No single star can be indicted as parent. The object likely spent millions of years drifting, a cold ember ejected by planet formation around some sun that now sits far from this corridor. The trajectory is a biography without a childhood photo, and that absence becomes part of the tone that surrounds it. Risk models lean over the shape to explore corners that ordinary narratives skip. One corner is the possibility of fragment trains. A fragile body can fissure near perihelion, and fragments can adopt slightly different hyperbolas that trail along the parent path. Those offset lanes cross the ecliptic at slightly different times. In the improbable case that a fragment aligns, the speed at atmospheric entry would be extraordinary. No crater table prepared for typical asteroids quite fits. Kinetic energy scales with the square of velocity, so a small boulder at 70 kilometers per second can rival a much larger domestic rock. Trajectory therefore feeds not only the romance of an origin story, it feeds the arithmetic of consequence. Another corner is the intersection with meteor science. Even if the nucleus misses by a comfortable margin, the trail of tiny particles released along a hyperbola can intersect a planetary orbit later. The date of nodal passage becomes a forecast for possible meteor activity, not from a periodic stream that returns each year, but from a one-time crossing that might seed the atmosphere with a sudden, sharp rain. The geometry must be kind, and the solar wind must cooperate in not sweeping the finest grains outward too quickly. The equations are cautious, yet the possibility transforms a clean flyby into a more textured encounter where the sky itself becomes the detector. Beyond calculations, the simple fact of a hyperbola alters human tempo. The short residence time forces a cultural sprint, a rush that is rare in observational astronomy. Schedules are cleared, instruments retuned, proposals accelerated, because the path will not bend to suit a calendar. Trajectory compels deference. It dictates who can see, when they can see, and how close they can get to certainty. In that sense, the numbers do not merely describe a motion, they choreograph a planet's response. The curve draws nearer to the sun, then slips by, then climbs outward toward a different winter. The story of the path remains behind as a record of how the visitor moved through a system that could not claim it. The elements at epoch will sit in a catalogue, the uncertainties will shrink to a final set of digits. The line drawn on the page will be a lesson for the next time a fast point appears. The biography in numbers will stand complete for this traveller, and the question that animates hazard analysis will pivot from where to what, and from what to how, it might share or shed material as it leaves. Uncertainty arrives first, not certainty. A fast point on a sensor becomes a column of numbers, and that column breeds a cloud. The cloud is statistical rather than meteorological, a three-dimensional fog in the space of possible orbits. Inside that fog live many worlds that almost match the same observations. Outside it wait worlds that do not. Analysts give the fog a more precise name. They call it a covariance, a way of compressing the imperfections of measurement into a shape that can be pushed forward in time. The shape is not round. It stretches into a long tube whose axis traces the best fit path, thin where the data are strong, fat where the future can still diverge. The reasons for thickness begin at the detector. Seeing smears the light, wind shakes the telescope, and pixels offer a grid that is never perfectly aligned to the sky. A centroid algorithm reads brightness and guesses where the center of a moving point should be. If the object is so faint that it skims the noise floor, that guess wobbles. If the sky background is uneven, the wobble grows. A fast traveller streaks a little during each exposure, and that streak must be modelled or it will drag the measured position along its trail. Star catalogues help by anchoring astrometry to known reference points, yet even the finest catalogues carry tiny biases in crowded regions, or for stars with unusual colours. Each little flaw breathes into the same fog. The first night produces a path that could be many paths. A second night begins to squeeze the cloud into a slimmer tube. Add a third, and the tube remembers curvature, instead of mistaking a straight line for a shallow bend. Even with 3 nights, there remains a family of solutions that may differ in speed by small increments that grow into large offsets over a few weeks. Uncertainty rides the square of time. A milliarc-second of positional error at discovery can expand into thousands of kilometers by the time the traveller dives around the Sunday. The mathematics are unforgiving and beautiful. Propagate the covariance with the same equations that move planets, and the fog exhales into a corridor through space and time. Risk work begins with that corridor, because the worst thing hides in the narrowest slice that still intersects a planet. Analysts build a swarm of virtual clones, each one a fully fledged orbit, perturbed from the best solution by random draws from the covariance. The clones are not fiction. They are parallel biographies, any one of which could be the true path within the limits of the data. Integrators march the swarm forward under the tug of the Sun and the major planets, sometimes with the Moon, sometimes with radiation pressure for dust-sized fragments, always with relativistic corrections where light and gravity insist on exactness. At chosen checkpoints, the swarm is mapped onto a plane that cuts the future encounter geometry at right angles, A-B plane for those who inherit celestial mechanics from a long line of precise minds. On that plane, the corridor becomes an ellipse or a streak, and the world's position appears as a point that does not move. What matters is the separation between the streak and the point, and how that separation tightens as nights add their photons. Not all uncertainty is born equal. Some is random, a dice roll with each exposure. Some is systematic, a bias that propels every measurement in the same wrong direction. A faint coma can draw the centroid away from the true nucleus if the data reduction treats the object like a star. Experienced teams respond with trailed point spread functions, and with masks that suppress the tail before the center is fit. Differential refraction at low altitude can shift positions when the color of the object differs from the stars that define the frame. Tools compensate when they know, but compensation works only as well as the model. The corridor records the truth of all this, without drama. It widens when ignorance rises, and it tightens when care removes a bias that had been quietly moving every point the same way. An interstellar visitor complicates the picture by inviting forces whose strength is not known in advance. Outgassing can push a small body with jets of sublimating ice. Celestial mechanics absorbs this by adding 3 parameters that describe accelerations along radial, transverse, and normal directions. The parameters are fit from the same data that build the orbit, and the fits are fragile when the time arc is short. Include them too early, and noise masquerades as thrust. Exclude them too long, and a real push tilts the corridor in a direction no one expects. The solution is simple and exacting. Keep observing, then test models with and without non-gravitational terms, and compare the way each predicts new positions. The model that predicts tomorrow better earns the right to describe yesterday. One instrument can shatter uncertainty if geometry allows. Radar paints a moving body with radio and reads back range and range rate with exquisite precision. A single echo can collapse kilometers of cross-track uncertainty to a ribbon. For a visitor that passes far outside the radar reach, that tool stays in its holster and the community looks to other gifts. Stellar occultations can do more than tell size and shape. A precise chord across a star pins position on the sky with a sharpness that rivals the best imaging. Photometry contributes by revealing rotation, which allows dynamical models to account for the way solar heating and vents might tilt pushes during the hours around closest approach. As the corridor evolves, a quiet vocabulary governs decision-making. The minimum orbital intersection distance to Earth is watched. Its uncertainty is watched more closely than its nominal value. The derivative of that distance with respect to time tells whether key geometry is improving or decaying. Keyhole is a term borrowed from cases where small gravitational bends can set up later encounters. For a single pass, a different image suffices. Think of a pencil-thin channel within the broader corridor. If the world sits inside that channel at the right hour, a fragment could enter the atmosphere. The channel is usually empty of the world, and usually the time is wrong, and usually fragments are not launched along exactly the lane that aligns with danger. Usually as a comfort that gets stronger with each new observation, scientists carry the corridor into communication with care. They borrow scales to keep language disciplined. The Torino and Palermo scales were built for bound asteroids with long lead times, yet the scales still offer a grammar for probability multiplied by consequence. Early values are deliberately dull, because early probabilities are dominated by uncertainty rather than fate. Values change as the tube tightens, and forecasters plan threshold statements in advance to avoid improvisation that would confuse the public. Transparency matters. So does rhythm. Frequent small updates that reduce the corridor are easier on nerves than rare dramatic ones that leap across orders of magnitude. The corridor does not live only in the sky. It threads through other systems that depend on predictability. Satellite operators watch for dust environments that might grow along the path. A fragile nucleus that sheds grains can build a curtain that crosses orbital altitudes days or weeks after the nucleus has gone. Models take gas drag near release, radiation forces afterward, and electromagnetic coupling for charged grains, and they pour that into maps showing where and when a haze might pass. Those maps are corridors of a different kind, guiding protective modes for hardware that cannot afford sandstorms in space. Underlying every refinement is a quiet revolution in reference frames. Modern astrometry leans on catalogues whose precision was unthinkable when the first asteroid networks learned their craft. Parallax and proper motion are known for 1 billion stars. Aberration, relativistic deflection near the Sun, and light time corrections are applied with a rigor that erases entire classes of former error. With those removed, what remains is closer to truth, and the corridor narrows because the floor beneath every measurement is more level than it used to be. A last, humbling feature of the corridor is its asymmetry in time. It shrinks more quickly forward than backward. The future responds immediately to each new constraint. The past resists, because the object lived under dynamics that the data did not sample. Ancient pushes and ejections are gone to memory. Dynamical origin remains a province of inference rather than proof. That same asymmetry makes prediction a more honest craft than reconstruction. The path tomorrow can be fenced to within a few hundred kilometers. The path in a different star's nursery will likely remain a suggestion. At some point, the tube becomes so thin that it no longer touches the planet's coordinates, even if pushed by conservative assumptions. The worst case exits the doorway not with a flourish, but with a quiet nod. Attention pivots to science rather than hazard. The corridor may still matter for meteor forecasts and for the choreography of instruments during the fast swing around the Sun, yet the part of the mind that hosted the sliver of catastrophe can return to other tasks. The mathematics has done what it was built to do. It walked into a fog and walked out carrying a map. The air in the rooms where that work happens feels different after such a walk. It is not triumph. It is relief, edged with the knowledge that the same corridor will be built again for the next fast light that stirs the detectors. Spectra arrive like postcards from a cold frontier. Each postcard is a thin line of brightness stretched across wavelength, annotated by dips where atoms and molecules have taken their share. Telescopes turn mirrors toward the hurrying point, and the night breathes through slits into instruments that separate color with crystal and grating. Observers nod to ritual. A solar analog star is recorded first, so that the sunlight reflected from the traveler can be divided by a proper reference. Air glow lines are mapped and subtracted. The telluric water that lives in every breath of Earth's atmosphere is modelled and removed, so that any water that appears later on the page can be claimed by the visitor rather than the home of the instrument. The first low-resolution pass is cautious. The continuum looks featureless and faint, yet not entirely mute. In the blue and near ultraviolet, where carbon chains would sketch familiar signatures, the expected bands hide. The violet CN group near 388 nanometers is harder to praise than to confirm. Observers keep their voices even. Non-detection does not mean absence, it means a limit for now. At longer wavelengths, the story begins to lean. Near 3 microns, a shallow trough suggests carbon dioxide absorption. Near 4.7 microns, carbon monoxide hints at a stronger appetite for sunlight than water would require at the same distance. The ratios whisper of a kitchen where ice is condensed under colder rules, perhaps in a region dominated by shadows and starlight rather than a warm nursery. A different set of eyes focuses on the familiar water bands near 1.5 and 2.0 microns, and on the broad 3.1 micron feature that usually marks the stretch of HO bonds. The sine wave that tells everyone a comet is awake. The features are subdued. The line that usually rises like a choir is more like a hum here. Thermal models agree with the tone. At the current heliocentric distance, carbon monoxide can sublimate from pores with vigor that water cannot match. If the engine is CO-rich, The pressure that sculpts jets and the force that tilts the path will record a different rhythm than the one assumed by tables built for domestic comets. Polarization adds color that spectra alone cannot provide. Sunlight scattered by tiny grains becomes partially polarized, and the fraction grows with phase angle. The curve of that growth is a fingerprint for grain size and porosity. Measurements taken at several angles suggest a population of highly porous particles, perhaps fractal clusters that formed gently in a low collision environment. Such aerogel-like fluff would feel radiation pressure more strongly than ordinary dust, and its interaction with the solar wind would carry a different coupling. The implication feeds quietly into hazard arithmetic, since a tail made of feather-like grains can sweep across space like a veil that extends farther than brightness alone would imply. High-resolution work begins as photons accumulate. The aim is isotope. The ratios of deuterium to hydrogen, of carbon-13 to carbon-12, of nitrogen-15 to nitrogen-14 hold stories about the temperature and density regimes where ice is condensed and were later processed. A clean measurement of D over H in water is ambitious at the brightness available, yet spectroscopists press their luck in the 2.7 to 3.2 micron region. A tentative number sketches a value lower than the average measured in long-period comets from the Oort cloud. If that number survives more nights, it would argue for formation in a colder or different pressure environment, one that left hydrogen less inclined to cuddle deuterium in the final mix. Visible reflectance slopes are folded into the dossier. Some comets are deeply red, their surfaces weathered by radiation into tholins that stain the spectrum. Others are neutral or slightly blue, their colors moderated by fresher exposures or different macromolecular blends. The slope here leans toward neutral, with a gentle turn to the blue in the ultraviolet. That tilt points to a surface that may have been resurfaced recently, by micro-impacts or by sublimation that pulls dark mantles aside to reveal paler crusts. A neutral or blue trend also changes how light pressure nudges grains, and therefore where a particulate tail might wander across interplanetary lanes. Mid-infrared photons, chased by space telescopes above the atmosphere, carry thermal information. The warm lump of the nucleus radiates as a simple object would, but the FIT prefers a beamed surface that concentrates emission rather than a smooth Lambertian spread. That preference signals a landscape of pits and vents, microtopography that can anchor jets. The effective size derived from thermal flux and assumed albedo suggests a nucleus in the modest category. Not a mountain, not a pebble, a city-scale body that could shed copious dust if friable, or remain disciplined if crusted with sintered ice. The albedo itself refuses to be high. Darkness remains the rule for surfaces baked by cosmic rays and micrometeorites between suns. A conference called Titan's Language. Observers choose words that navigate between caution and clarity. Carbon monoxide, likely present. Carbon dioxide, likely present. Water weak relative to those at current distance. Carbon chain bands depleted compared to typical comets in the inner system. Polarization consistent with porous aggregates. Thermal emission consistent with low albedo and roughness. Each clause becomes a brick in a structure that will support the next set of claims. A taste of the exotic enters through a narrow window. Nitrogen ice, in its pure state, carves a subtle signature near 2.15 microns when observed at the right temperatures. Pluto shows this feature in spectra gathered by patient instruments that stare for hours. Here, the signal is almost lost, yet a small depression aligns with expectation. The hint invites restraint. A tiny admixture of methane or ethane can counterfeit that trough. Still, if even a thin film of nitrogen frost coats parts of the surface, the sublimation behavior at perihelion will surprise. Nitrogen turns to gas with enthusiasm at temperatures that water considers chilly. Venting would begin far from the sun, and any fragment that breaks loose would feel a push early in the approach. Chemical inventory offers more than origin stories. It writes marginal notes on risk. Carbon monoxide-driven jets can switch on in the outer system, steering the nucleus by small accelerations for long intervals. That kind of steering complicates forecasts of minimum distance and timing, not by orders of magnitude, but enough to matter when planning tight windows for radar beams, occultation stations, and satellite-safe modes. A coma dense in CO and CO could load the upper thermosphere with molecules that carry different ionization pathways than water-dominated plasmas, altering how a tail couples to the solar wind near Earth's orbit. The numbers likely stay small, yet grid operators and satellite controllers prefer numbers that have been measured rather than imagined. Dust composition follows the gas. Polarimetric and spectroscopic signs suggest a scarcity of the small carbon chains that perfume domestic comets, and a relative abundance of simple volatiles that complain at lower heat. That blend hints at a nursery where ultraviolet radiation was gentle, or at a long interstellar drift that sanded away fragile organics and left only stubborn backbones. If grains are rich in CO and CO-driven frost, then the critical size for survival in sunlight shifts downward. The dust size distribution would tilt towards submicron particles that scatter blue light, a behavior that the reflectance slope already teases. Such grains charge quickly in the solar wind and dance to the tune of magnetic fields, making tails broader, softer, and more capricious. Laboratories on Earth race to match the sky. Cryostats are charged with ices grown at carefully chosen temperatures. Mixtures of carbon monoxide, carbon dioxide, nitrogen, methane, and water are layered in thin films, then irradiated to simulate years in the dark between stars. Spectra of these films are compared to the faint features recorded by telescopes, and models are tuned to learn which recipes reproduce the postcard dips. The experiments are not entertainment. They decide whether a shallow trough can be claimed by a molecule, or must be returned to the noise. They also teach how thin crusts evolve when warmed, whether they crack into polygonal mosaics that vent suddenly, or relax into steady exhalation. A final note in the chemical ledger speaks of heat capacity and fracture. Ices that escape at low temperature pull energy from their surroundings with greed. The resulting cooling can deepen stress already seeded by rotation and by the gradient between sunlit and shaded faces. A body laced with CO-rich pockets might shed shells or slabs as it nears its closest pass, even if water remains locked. That behavior would feed fragment trains. It would darken the coma with slivers large enough to survive a while as independent bodies. It would test how well the hazard models handle non-uniform eruptions. A composition far from the local norm does not raise the odds of catastrophe by itself, yet it writes a more intricate script for how the passage plays out. Nothing in the spectral record insists on miracles. The measurements show a natural chemistry for a world raised in slightly different cold. Natural does not mean familiar. The balance of gases is tilted, the grains are more open, the colours less red, the engines primed to run at distances where water sleeps. That combination is sufficient to seed a new branch on the tree of comets. It is also enough to keep the calculators honest when they project the path and the plume. In the end, the postcards from the frontier accomplish what they always do. They replace conjecture with texture, and they invite careful minds to translate texture into motion, pressure, and light. Invisible hands can steer a small body without leaving smoke or scorch. The steering lives in sunlight, in vapor, in heat that takes flight as photons. Dynamics names these hands with quiet terms, non-gravitational accelerations, and then splits them into directions tied to the path. Radial along the sunline, transverse along the motion, normal perpendicular to the orbital plane. 3 components, each drawn as a modest whisper, together able to move a traveller by thousands of kilometres over weeks. No plume need be seen. The influence writes itself into the timing of a point of light as it crosses a detector, night after night. Gas is the first suspect whenever a comet-like surface warms. Sublimation pushes like a fleet of tiny rockets. The push grows where sunlight lingers, fades in shadow, and sometimes erupts where fractures open vents. If the surface is patchy, the thrust is asymmetric, so the net force follows whatever geography survives until the next crack. Modelers fold the push into a function that grows with solar proximity, then solve for 3 numbers that scale the effect along the radial, transverse, and normal axes. When those numbers predict positions better than gravity alone can manage, a case builds for outgassing that leaves little direct trace in low-resolution imaging. Heat itself can push. A rotating object warms and cools across its day, and the thermal photons that depart carry momentum. When the afternoon side emits slightly more than the morning side, The recoil nudges the path forward or backward a hair. This is the Yarkovsky effect, a slow persuasion that matters over years for asteroids, and over shorter spans if a visitor loiters, which it does not. Yet near perihelion, when the thermal wave runs shallow and the rotation state keeps one hemisphere hotter for longer, even a brief thermal imbalance can add to the bookkeeping. The cousin of this effect, a torque that changes the spin rate, can spin up or spin down a nucleus. If spin climbs toward the limit where cohesion fails, fragments can peel away. Rotation becomes a lever that pries the body into pieces, changing the mass and the way gas escapes, which changes the forces again. Light pushes more directly through radiation pressure. Dust grains with a large area relative to mass feel the pressure strongly. If the nucleus is covered in a skin of delicate aggregates, grains can lift free and drift, and their departure takes momentum that tugs the parent. If layers crumble into foamy sheets that curl with heat, the effective area to mass ratio of those sheets can mimic the behavior of a sail. No exotic material is required, only geometry and brittleness. Yet, the result in the astrometry looks like a gentle shove that never shows a visible engine. A thin flake turning in sunlight can generate forces that scale in ways not captured by simple gas laws, and the spin of such a flake can average the push into a steady bias. Electrons and ions add their own choreography. A coma becomes a laboratory where dust gains charge under ultraviolet light. Charged grains couple to the solar wind and magnetic field. The coupling is weak for boulders, strong for specks, but intermediate sizes can walk a strange middle path. They drift along field lines, they are picked up and pushed sideways, and the electric field of the moving plasma exerts a drag that depends on charge and size. The nucleus feels little of this directly, yet the pattern of mass loss is shaped by the plasma environment. When loss is directional, the nucleus recoils in response. The dance between gas, dust, and fields can therefore write a small acceleration into the nucleus without a single bright jet to advertise it. Geometry complicates everything. A tumbling object does not present the same face to the sun as it rotates, so the vector of any thrust swings around, often faster than a day on Earth. If the tumble is complex, the thrust averages out differently than if spin were simple. Phase of rotation at closest approach matters. Longitude of active patches matters. Shadowing by ridges matters. Thermal inertia matters, because a surface that hangs onto heat sends photons later than noon, sliding the average push off the sunline. The superposition of these effects creates a fingerprint in the timing residuals, the tiny differences between where pure gravity would put the dot and where telescopes actually find it. A difficult case arises when the measured acceleration scales with sunlight, but gas lines remain faint. That pattern invites alternate microphysics. Hydrogen released from water ice by trapped heat can escape as H atoms that leave almost no spectral signature, yet still carry momentum. Fractured ices can sputter, not vent, a mist of nanograins that scatter little and push much. Brittle organics can crack and desorb molecules that ultraviolet dissociates before they can build a line. These pathways make forces without obvious footprints in the classic bands of comet chemistry. Laboratories can simulate some of this behavior, but the scale and complexity of a real surface elude any chamber. Torque deserves special caution. A small, uneven thrust can twist a nucleus in ways that grow nonlinearly. Spin-axis precession changes the season of each vent. The change season alters which vents lead, which lag, which choke, which open. Over a few rotations, the entire pattern of pushing can reconfigure. The effect in the orbit solution looks like a non-gravitational acceleration that wanders in phase and amplitude. If the data cadence is sparse, the solver may attribute this to noise or fit spurious constants that happen to reduce residuals. Only dense, multi-night astrometry, paired with light curves that map spin, will uncover the true choreography. From a standpoint of risk, these invisible hands matter because they tilt the corridor of uncertainty. A small transverse push moves the predicted time of closest approach. A small normal push changes the distance by a margin that can decide whether meteorologists prepare for a sharp, short-lived shower of dust. A change in spin that leads to fragmentation injects new bodies into neighboring lanes. The fragments inherit the parent velocity, with tiny offsets that grow into large separations over weeks. Those offsets can set up a crossing with Earth that the intact parent would never have delivered. Ethics and engineering intersect when forces without footprints are invoked in public language. If the models prefer a shove that lacks a clear chemical signature, audiences may reach for stories that delight in the exotic. Responsible voices keep the story grounded. Sunlight carries momentum, and surfaces shed it. Heat flows and departs. Gas escapes through pores and scars. Shape matters, spin matters, porosity matters. Put these together, and a small bias in motion is a natural outcome. Speculation about thin artificial sails is reserved for seminars where numbers are tested, not for headlines. Clarity is part of preparedness, since fear amplifies ambiguity. Observation strategy adapts to this subtlety. Astrometry spreads across long arcs before and after perihelion to catch how the acceleration grows and fades with distance. Photometry resolves rotation and reveals changes in period that would betray torque. Spectroscopy keeps watch for faint lines that might rise as distance dwindles. Polarimetry maps grain populations, so radiation pressure can be estimated in real time. Occultations pin positions with chords that are not easily fooled by coma asymmetry. Each method narrows the space in which invisible hands can hide. Numerical experiments close the loop. Thousands of clone orbits, each endowed with small thrusts that follow different laws, are marched forward. Some use a sublimation law that rises with solar flux. Some use a constant radiation pressure term, tied to a hypothetical area to mass ratio. Some add a stochastic component that imitates vents switching on and off. The family that best predicts future measurements earns confidence. The same family then feeds hazard scenarios. If that family allows fragment release at specific distances, the timing of potential dust lanes crossing Earth's orbit can be forecast with useful bounds. If it implies a sustained transverse acceleration, the minimum separation can be updated with humility and precision. In the end, the lesson is simple and austere. Gravity sets the stage, but sunlight writes footnotes that can shift outcomes. The shifts are small in force and large in consequence because time multiplies them. Worst cases rely on small chances and precise alignments. Yet small chances deserve measurement, not dismissal. Forces without footprints remind every watcher that the quiet parts of physics do not announce themselves with spectacle. They hide in residuals, in the seconds by which a point arrives early or late. To see them is to respect them. To respect them is to plan for the slim branches of the future that they might nudge into being. Perihelion is not a place but a temperature written on moving stone. Light rises with the inverse square of distance, and a cold nucleus enters a kiln where every facet learns a new arithmetic of heat. Subsolar patches sprint toward equilibrium, while night-side terrain lags, so gradients sharpen across meters and even centimeters. Thermal skin depth remains thin for the hours-long day of a small body, only a few millimeters to centimeters depending on conductivity and spin. Within that shallow layer, expansion fights cohesion. Microcracks lengthen grain by grain. Fractures that slept through distant space awaken to a chorus of clicking stress, and each click primes a vent. Vents change everything. Sublimation fronts climb toward the surface along pores and fractures. Gas accelerates through tortuous passages, transitions from diffusive to free molecular flow, and bursts into vacuum with a pressure that can lift dust. Drag overcomes gravity once grains are small enough, or cohesion weak enough, and a curtain of particles departs. The curtain becomes a coma that thickens with each hour of approach. It is not uniform. Cliffs and pits collimate the outflow into jets that spin with the nucleus, creating a slow pinwheel traced in sunlight. Where crusts are thin, chambers overpressurize and fail, producing brief geysers. Where crusts are thick, sublimation undermines support, and entire ledges slump, exposing fresh ice that fuels a second wind. The surface does not merely erode, it evolves. Sintering welds grains where warmth lingers, knitting a temporary shell that can throttle gas until it cracks. Frost migrates from hot zones to cold shadows, painting walls that face away from the sun with thin films of volatile ice. Those films become morning engines when rotation swings them into light. Near perihelion, this redistribution repeats many times per rotation, shaping a mosaic of active patches whose timing matters as much as their size. Every new patch adds its own push, and the sum of pushes writes a small bias into the path that cannot be ignored during closest approach. Spin moves under this weather. Outgassing torques act where jets are offset from the center of mass, and the rotation period can drift by measurable amounts within days. If torque accelerates spin toward a critical value, tensile strength becomes a headline. Cometry material can hold together with strengths measured in tens to hundreds of pascals. That is sandcastle territory. Past the limit, equatorial ridges shed slabs, tips of bilode shapes separate, and boulders once locked by frost slide downslope. Fragmentation then reshapes the coma, adding slow-moving companions that trail along neighboring tracks. Each companion inherits momentum plus a small offset. In the language of consequence, that offset grows with time and can matter long after the nucleus has turned the corner around the Sunday. Tidal force plays a quieter role unless the track dips very low, yet it is present. Near the star, differential gravity tugs more strongly on the near side than the far. For rigid rock, the effect is modest at ordinary perihelia. For fragile aggregates threaded by ice, it can help existing fractures to lengthen. If perihelion sits within a few stellar radii, tides rise toward the sort of pull that ripped earlier sungrazers. Most visitors stay well outside that regime, but the calculation is always run because tidal terms can tip a marginal structure into failure when combined with heat and torque. The coma's chemistry changes pace under the heightened flux. Water's lifetime against photodissociation shortens to hours. Carbon monoxide and carbon dioxide are stripped in comparable spans, and the resulting atoms and ions feed an ion tail that becomes a long, thin antenna for space weather. Sodium can escape from grain rims by thermal desorption or sputtering, adding a faint, narrow tail that points almost exactly away from the Sunday. The plasma environment grows electric. The solar wind wraps a magnetic drape around the obstacle of an expanding ion cloud, and currents set up along the flanks. Coronal mass ejections turn that drape into a snapping flag. Disconnection events cut an ion tail and let it regrow, as if the comet were exhaling ribbons at the rhythm of the sun's moods. Dust at perihelion undergoes its own winnowing. Radiation pressure accelerates the smallest grains most strongly, sorting the coma by size. The parameter that measures this sorting, the ratio of radiation pressure to solar gravity, grows large for submicron fluff. Those particles peel away rapidly and sweep into wide fans. Larger grains hang close and form a dense spine along the track. Their fates diverge. Fine motes become the grand, soft architecture seen in wide field images and can be deflected significantly by solar wind fields. Coarser grit writes the seeds of a meteoroid stream that can intersect planetary orbits long after the nucleus departs. Perihelion decides the stream's density. A brittle crust that fails in slabs feeds boulder-scale fragments. A porous skin that erodes gently feeds a haze. The difference sets the stage for either a sharp, brief meteor storm years later or a mild background of sporadic meteors. Inside the nucleus, heat opens a dialogue between materials with different heat capacities. Carbon monoxide frost consumes energy greedily as it escapes, chilling neighborhoods that would otherwise warm. Water ice, once engaged, releases vapor more sluggishly and deepens pores as it leaves. Organics soften, then char, then toughen into stubborn mantles that can either seal in gases or crumble into dark powder. Voids widen where ices retreat, roofs collapse. Some cavities become skylights into caverns, their rims scalloped by retreating frost. Others remain sealed until pressure finds a seam. Outbursts that follow can be dramatic without warning any camera a minute before they happen. The perihelion geometry also controls what can be seen. Solar elongation for observers on Earth shrinks during the days closest to the turn, and ground-based telescopes lose access in bright twilight. Reliance shifts to spacecraft with coronagraphs and heliospheric imagers. Instruments that watch the corona for eruptions catch the passing nucleus and its tail in silhouette against solar wind structures. These views are crude in spatial resolution but rich in context, showing how the tail bends during gusts and how disconnections ripple outward. coordination between heliophysics and planetary science becomes essential. The same cameras that warn of a flare can reveal whether a dust fan has broadened into zones through which satellites will pass later. Hazard thinking reaches for specifics. If a large fragment detaches and lags, its hyperbolic arc will sit just behind the parent dot. Should that arc slice the ecliptic near a planet's position days later, the entry speed would be startling. Kinetic energy rises with the square of velocity, and entry at 70 kilometers per second writes a different airburst profile than the familiar asteroid case. Thermal pulse, shock coupling, and altitude of peak brightness all shift. Planners translate those shifts into ranges at which windows fail, into ground footprints where sonic booms could startle infrastructure, into altitude bands where satellites risk hypervelocity dust. The probabilities remain small, yet each parameter draws a box where responses would live if luck ran thin. Not every stress at perihelion is violent. Some are cumulative. Pitted terrain grows deeper pits with each pass around a sun, whether that sun is ours or one left behind. Volatile depletion alters future behavior. If the present visitor is on its first and only dance through strong light, its surface may still hold tender reservoirs that erupt easily. Afterward, those will be reduced. The comet that leaves is not the comet that arrived. It departs leaner, rougher, threaded with scars that record which vents sang and which were silenced. That record will influence non-gravitational drifts on the outbound leg, so the final tweaks to trajectory must be measured rather than guessed. There is a counterpoint to fracture and loss. Consolidation can protect. Where sintering welds grains into crusts, erosion slows. Where recondensed frost cements walls in shadow, caverns endure. Regions that align poorly with the sun during the critical days escape the worst heating and become islands of durability. The result is topography that preserves the history of perihelion in layers and ledges. If a spacecraft ever finds such terrain, it will read the striations as a seismograph would, pulses of stress frozen into stone. Perihelion ends as quickly as it begins. The furnace cools with distance, and activity ebbs in a reversible fade. Jets thin, light curves quiet, and torque relaxes. The coma contracts and clarity returns to astrometry. What remains is inventory. Mass lost, fragments made, stream seeds launched, spin altered, shape revised, tail chemistry archived, space weather interactions logged. This list is not an epitaph. It is an accounting of transformations that determine what the traveller now is and what relics it has deposited along its path for worlds and machines to encounter. The crucible does not promise catastrophe. It promises change under rules that are firm and sometimes surprising. Temperature gradients, gas laws, brittle mechanics, photon momentum, and plasma play together in a brief concert near the Sunday. In that concert, the loudest passage is not always the one that matters most. A single slab splitting from a ridge can mean more downstream than hours of steady dusting. A minor torque can tilt a later outgassing season into a new pattern that alters timing by hours. Perihelion is therefore the hinge on which the rest of the narrative swings. It is the moment when the invisible interior becomes policy for the sky. Dust is the handwriting of a comet, a script the vacuum can read from millions of kilometers away. When grains lift free, they stop belonging to rock and begin belonging to laws that trade mass for lightness. The newborn cloud is not a mist of identical specks. It is a choir with voices from nanometers to centimeters, each size obeying a slightly different conductor. Some pieces are round, grown by gentle accretion in a cradle of frost. Others are acicular shards, etched by thermal fracture, needle-like splinters with length far greater than width. A few are plates and foils torn from sintered crusts, thin enough to flutter under photons. Composition varies as well. Silicates carry magnesium and iron. Sulfides hide metallic luster. Carbon-rich mantles darken many surfaces. Every combination of shape and material writes a different response to sunlight, plasma, and gravity. Charging begins the moment daylight reaches a grain. Ultraviolet photons kick electrons from surfaces, leaving a positive potential that grows until emission and collection balance. Secondary electrons splash from grains struck by hot particles in the solar wind. Ambient electrons and ions then gather unevenly across complex shapes. A needle builds stronger fields around its tips than its waist, so charge concentrates at ends, like frost on thin grass. In darkness, the polarity can reverse as electrons dominate, transition regions around the terminator of a rotating grain host miniature storms of current. These tiny circuits matter because they change how a grain feels the magnetized wind, and because they alter the ease with which molecules stick or desorb. Dynamics follows with a calculus that is simple to state and rich to solve. Solar gravity pulls on mass. Radiation pressure pushes on area. Their ratio is the parameter that dust physicists call beta. For compact sand-sized grains, beta is small and the sun wins. For porous fluff and ultrafine motes, beta rises. When beta approaches unity, the push and the pull nearly cancel. When beta exceeds unity, the grain is blown outward as if the star were a fan rather than an anchor. A hyperbolic parent can therefore seed 3 families at once. Large fragments behave like tiny comets, scattering along the parent trajectory. Mid-sized grains enter wide, skewed ellipses that may cross planetary lanes months to years later. The lightest become a fountain that streams away from the star on paths that ignore orbits and paint space with a barely visible haze. Charged grains add a new force to the balance. The Lorentz term bends their motion around the magnetic field that rides the solar wind, a spiral that opens like a rotating lawn sprinkler from the spinning sundae. Small, highly charged particles execute wide gyromotions while drifting with the wind. Their paths are neither straight nor Keplerian. The field guides them into sheets and filaments that can detach and reconnect when solar storms pass. Observers know these features as striae and rays in a dust tail, delicate ribs and spokes that appear and fade with the moods of the heliosphere. Needles feel this guidance more strongly than spheres of the same mass, because their charge-to-mass ratio is larger and because their shape aligns with the field more efficiently. Collisions within the cloud are rare but transformative. Fractal aggregates can compact when they touch, increasing density and lowering beta. Needles can splinter into shorter fragments that retain sharp ends and high aspect ratios. Sintering can weld contacts where sunlight warms junctions. Sublimation of icy cements weakens bridges and lets clusters shed members into a finer spray. The cloud evolves as it moves, and the evolving cloud changes how it interacts with light. A coma that starts grey can turn blue as the smallest grains dominate scattering. A tail that begins narrow can broaden when charging increases, and grains respond more strongly to fields than to gravity. Orbits for dust are a geometry of differences. A slight reduction in effective gravity due to beta can turn an escaping path into a bound ellipse. A faint push from the parent's last jet can separate a grain by enough meters per second to change the date it reaches a node where Earth may be. Pointing Robertson drag, a gentle loss of angular momentum as photons carry off a little energy, slowly spirals bound grains inward. Resonances with Venus or Earth can trap some sizes temporarily, piling particles into rings that ride just ahead of or behind a planet's position. A hyperbolic source will not feed a ring for long, yet a single rich shedding can leave a measurable ripple in the zodiacal light as sunlight scatters from a fresh band of dust. Hazard lives in flux, multiplied by speed. A grain the size of a pinhead, impacting a satellite at tens of kilometers per second, carries enough energy to pit a radiator or shatter a lens coating. A shard with needle geometry concentrates force along a tiny contact area. Multi-layer insulation can be pierced by a spike that a sphere of the same mass would only dent. Whipple shields, the workhorse armor that vaporizes incoming particles against a sacrificial bumper, are tested against distributions typical of the meteoroid environment. A temporarily elevated flux, rich in high aspect ratio fragments, rewrites expectations for ejector sprays and penetrations. Star trackers can be blinded by a single bright streak. Radiators can leak. Solar cells can suffer from tiny craters that shadow active material with molten glass. Different orbital shells face different risk. Low Earth orbit benefits from atmospheric drag that sweeps many particles down within weeks, but it also hosts the densest fleet of vehicles. Hypervelocity collisions produce debris that complicates traffic management even after the dust stream itself has thinned. Medium Earth orbit holds navigation constellations whose timing must not drift. High-altitude crossings through a broad dust fan can trigger transient increases in single-event upsets as tiny impacts, liberate charge, and secondary electrons near sensitive circuits. Operators plan for solar storms. A dust storm is rarer, quieter, more mechanical, and it demands different checklists that include slewing sensitive faces away from the expected radiant and adopting safe attitudes that reduce cross-section. Atmospheric entry for the finest grains ends not with luminous streaks but with chemistry. Most particles smaller than a few tens of microns ablate high above weather. Metals oxidize and recondense into nanometer-scale smoke in the mesosphere. These meteoric smoke particles seed noctilucent clouds and participate in catalytic cycles that affect ozone and odd nitrogen. A sharp, short-lived injection from a fresh trail modifies those cycles by a tiny percentage. Climate does not notice at the surface. The upper air does, and radio waves threaded through that region can scintillate as gradients sharpen. Long-distance communication across polar routes occasionally feels such changes during meteor showers. A one-time storm from a hyperbolic source would write a brief, distinctive signature into ionospheric records. Ground-level risk from dust itself is negligible in ordinary scenarios. The air is an effective filter for everything except the largest fragments, and those announce themselves as fireballs that the sky patrols already watch. Indirect effects deserve a line in any complete ledger. A satellite struck at the wrong moment can fail and take a service offline. A cluster of failures during a dense crossing could ripple through timing networks. Aviation may reroute if forecasts predict intense ionospheric scintillation, not for safety in the cabin but for the integrity of signals that guide over ocean navigation. These pathways translate faint streams of grains into human experience without exaggeration. Models turn this into maps. Release is represented by time, speed, direction, and size distribution. Forces are applied according to beta and charge. The solar wind and magnetic field are set by observations and forecasts from heliophysics missions. The cloud is marched forward until it intersects the orbital corridors of spacecraft. The result is a set of probability contours across altitudes and longitudes, with dates and hours annotated. For a hyperbolic parent, the contours usually describe a single passage rather than a recurring hazard. The value of the map is not drama but allocation. Antennas can be stowed, instruments can be shuttered, non-essential maneuvers can be postponed. Mission teams can rehearse recovery from transient anomalies. Laboratories connect shape to consequence. Dust accelerators fire micron and submicron particles into target materials at several kilometers per second. Those speeds fall short of cosmic values, yet they teach scaling. Needles fracture into clouds of vapor and fragments whose size distribution differs from spherical projectiles. Shock cones in polymers, craters in glass, and charge yield in dielectrics all show dependence on aspect ratio. These results inform the shields that future satellites might carry if streams from interstellar visitors become less rare with broader surveys. A final thread ties beauty to caution. The same stream that threatens hardware paints the sky with meteors. Rates can rise to thousands per hour if Earth crosses a dense filament of coarse grains. The display would be sharp and brief, with fast streaks that start high and end high because high-speed grains ablate quickly. Cameras and eyes would remember a night that looks carved into the dark with silver lines. In the ledger, where outcomes are weighed, that memory belongs beside the mechanical precautions, because the worst that could happen is not the only story dust can tell. Earth moves along a narrow ribbon, a track of dates and longitudes that repeats with each year. Debris does not honor that repetition. Fragments released from a fast comet trace a looser river, broadened by the small differences that arise at birth. If a river and a ribbon cross in both place and hour, the sky writes sudden handwriting. The planet steps through a band of stones and sparks. Fragment trains begin as structure, not chaos. When a nucleus sheds blocks and slabs, the pieces inherit nearly the same velocity, then acquire tiny offsets from jets and tides. A meter-scale shard leaves with meters per second of difference, a boulder with far less, a chip with more. The small offsets become hours, then days of separation along the track. Solar gravity organizes the parade. Radiation pressure ignores the larger pieces and worries only the grains. The result is a string of siblings that occupy a corridor only a few thousand kilometers wide, a corridor that continues to widen with time. Prediction leans on that geometry. The orbit of each fragment cannot be measured directly, yet the family can be modeled as a cloud distributed around a parent path using a kernel of ejection speeds and directions. Analysts place this cloud in heliocentric coordinates, then compute where the cloud intersects the ecliptic at the ascending and descending nodes. The nodes are where crossings can matter. Earth occupies its own longitudes on a calendar that is clockwork precise. If the nodal crossing of the cloud and the calendar align within hours, the sky prepares a performance. If the alignment misses by days, the planet walks through emptiness, and only spacecraft far from the line feel a whisper of dust. Kinematics sets the tone of any encounter. A body arriving from interstellar space carries heliocentric energy that adds to Earth's motion or subtracts from it, depending on geometry. Relative speeds near atmospheric entry can sit anywhere from a few tens to roughly 70 kilometers per second. That upper bound is a hard limit set by the combined vectors of Earth's orbital speed and solar escape speed at 1 astronomical unit. Such speeds rewrite the arithmetic of energy. A 10-meter stone at 70 kilometers per second carries more kinetic energy than a significantly larger domestic rock at 20. The conversion of that energy into heat, light, and shock becomes the difference between a high-altitude flash and a ground-level event. Entry physics explains how that energy is spent. A fragment enters at a shallow or steep angle, meets air that thickens by scale height, and experiences dynamic pressure proportional to density and velocity squared. At interstellar speeds, dynamic pressure rises quickly. Most stony bodies begin to fragment above 30 kilometers altitude, many well above that. Ablation removes mass as heat peels away layers, then fragmentation multiplies the surface area, increasing heating further. Luminous efficiency at these speeds can be a few percent, so an object the size of a classroom can rival the sun for seconds as it breaks. The shock wave spreads as a spherical front, weak by the time it reaches the ground for small bodies, strong enough to rattle windows if the piece was several meters across and the trajectory angled toward a city. Iron behaves differently. Cohesive metal can carry load longer, descending deeper before breakup. Even so, at the highest speeds, iron suffers severe heating and mechanical stress. Small iron fragments survive to lower altitudes, sometimes to the ground, but most of the kinetic energy still goes into air. The fear of an ocean-generated wave from modest fragments is misplaced. Water absorbs the pulse efficiently for bodies under 100 meters. To disturb a coastline, a massive, coherent impactor must strike with the wrong geometry near a shelf. That scenario remains a statistical ghost when the source is a single brief fragment train. Observation and warning rely on instruments that watch all sky, all the time. Space-based infrared sensors record sudden blooms of heat in the upper atmosphere. Ground-based infrasound arrays hear the low tones of shock fronts rolling around Earth's limb. Radar sees ionization trails that persist long enough to be traced in 3 dimensions. Optical fireball networks, spread over continents, triangulate bright paths with timing accurate to milliseconds. These systems do not prevent entry. They record it and reconstruct it. For a narrow train, the first bright event creates an instant forecast for the next minutes, since fragments in the same string arrive along nearly parallel tracks, separated by the offsets they earned at release. Meteor storms belong to a different register, yet they share a foundation with fragment trains. A storm occurs when the planet intersects the dense central filament of a dust trail launched on a past perihelion. The rate can leap from background to thousands per hour. Tracks arrive from a radiant that appears to sit in one constellation for the night, though perspective hides a dynamic dance. In a case where the parent was interstellar, a storm would be rare and brief, limited by the fact that the trail does not repeat each year. The display would be startlingly fast. Many meteors burning at high altitude with short, fine streaks and minimal trains, because high speed removes mass quickly and excitation leafs through energy levels rapidly. Risk to machines and people during a storm is not the same as risk from meter-sized fragments. Eye safety for pilots can become a bullet point if cockpits face a radiant during the most intense minutes. Satellite operators may rotate vehicles to present minimal area to the incoming direction. Power grids do not mind light. They mind charged particles and geomagnetic change, so electrical systems watch the sun rather than meteors. Air traffic controllers can adjust routes to avoid increased ionospheric scintillation if navigation signals become noisy. In all these cases, preparation is a matter of timing and geometry, and timing is the gift that celestial mechanics yields when the nodal crossing is known in advance. Modelling tools owe a debt to the study of historical showers. The Leonid storms of the 19th and 20th centuries taught how filaments released in specific years remain compact for decades, then disperse. That lesson translates to any fast parent. A trail released near perihelion can remain sharply defined for 1 or 2 revolutions if the parent were bound. If the parent is unbound, the filament still retains coherence for months or years, then fades into the background of the zodiacal cloud. During that brief coherence, flux at Earth can spike for minutes when the ribbon and the river cross precisely. Predictive power rests in how well ejections, speeds, and directions were inferred from photometry and spectroscopy when the shedding occurred. Communicators face decisions when a potential crossing appears on calendars. Silence invites rumour, blunt alarm breeds fatigue, precise language sustains trust. The right posture is clinical. Rates per hour and energy per impact are presented with intervals that reflect uncertainty. Maps show ground tracks of expected radiance for different longitudes. Spacecraft teams receive private forecasts that resolve altitudes into risk bands, since a vehicle in medium orbit cares about a different slice of the stream than a probe near the Earth-Moon Lagrange points. Emergency managers are reminded that meteors do not poison air or water, and that the loudest effect on the ground from small bodies is usually a chorus of phone calls. If a larger fragment looms within the corridor, telescopes can sometimes catch it as a distinct point moving near the parent path. Radar ranges one if opportunity allows, although geometry often denies that chance. Light curves for such pieces, if they can be measured, reveal slow tumbling that implies weakness. A weak object breaks high. A strong, compact object remains a small probability on the tail of a distribution that favours rubble and frost. That tail deserves a plan, even if the plan is modest, consisting of airspace closures for a minute over an ocean track and notices to mariners who could be startled by a bright noon in the night. After any crossing, evidence falls. Tiny spherules collect on rooftops and in gutters. Their composition betrays extraterrestrial origin when nickel and cobalt ratios speak with an accent foreign to Earth's industry. Radar tallies residual ionization as a decaying sheet in the upper atmosphere. Infrasound records fade into the roar of storms. The intact pieces that survive to the ground are rare and sought by hands that know magnet to stone. Most of the mass returns to air as vapor and smoke, then settles invisibly into a planet that is always swallowing a drizzle from space. The lane continues after the meeting. Earth carries on, and the fragment river thins toward a future where its particles join the background. The worst that could happen turns out to be a cascade of small things in most cases: bright minutes in a sky, a few cracked panes, a handful of instruments that blink and recover. The rare, larger possibility remains a ruler for planning rather than a prophecy. Between the small and the large lies the real task, which is to predict the hour of crossing, to aim cameras and caution at the right patch of sky, and to accept that a planet travelling through a universe of stones will sometimes step into glitter. Speed is not just distance over time. At tens of kilometers per second, speed becomes a sculptor that carves air, stone, and water into shock and light. A fragment the size of a room carries a quiet face in darkness and a different self the instant it meets atmosphere. Molecules part, then compress into a shock layer so hot that chemistry forgets itself. Oxygen dissociates. Nitrogen follows. A sheath of plasma wraps the intruder and sings on radio frequencies while the object begins to shed mass like a tree in a hurricane. The arithmetic is simple to write and severe to feel. Energy equals 1/2 of mass times speed squared. Double the speed and the energy quadruples. A 10-meter stony fragment with density near 3,000 kilograms per cubic meter has a mass on the order of 1.5 million kilograms. At 70,000 meters per second, the energy approaches 1 megaton of TNT. Most of that energy will be delivered to air high above the ground, but a megaton in the sky is still a loud conversation with a city. Entry angle decides how long the conversation lasts. A shallow path lengthens the traverse through thin air, spreading heating over a greater distance and favoring fragmentation. A steep path shortens the traverse and raises the dynamic pressure quickly. Dynamic pressure equals 1/2 atmospheric density times speed squared. At 60 kilometers altitude, density is low, yet the square of 70 kilometers per second overwhelms that thinness. Stony material begins to fail when dynamic pressure approaches a few megapascals. That threshold is reached high in the mesosphere for fast entries. Failure rarely means one clean break. It is a progressive pancaking where the object flattens, flares, and multiplies into a cloud of incandescent debris that decelerates as surface area increases. Material identity sets the soundtrack. Porous, volatile, rich fragments behave like brittle foams. They ablate early, their interiors insulated by voids that collapse as gases escape. They burst higher and paint wide, pale fireballs with little ground impulse. Stronger, stony bodies hold longer, bursting lower and generating sharper shocks. Iron carries cohesion through greater loads. A 20-meter iron piece can push into the stratosphere before shattering, and a 50-meter iron piece can deliver a multi-tens of megaton event if geometry concentrates its release. Even then, most energy still couples to air rather than ground, but the footprint of overpressure widens and windows complain across many kilometers. Light from the fireball is not all wasted heat. Luminous efficiency, the fraction of kinetic energy that leaves as visible light, sits at a few percent for these speeds. Night becomes day for seconds. Shadows harden. Reflections slide across water like a false dawn. Ionization leaves a trail that radar can paint as a bright scar. The trail conducts and then diffuses. Communications along a great circle passing under the path can flicker while the plasma rearranges itself into the upper wind. Blast is the part that people remember. A shock front races outward from the burst. At distances where overpressure is a few kilopascals, unreinforced windows surrender. At higher overpressures, light roofs lift, weak walls bow, and small objects inside rooms become fast. The front arrives seconds after the flash and keeps going, ebbing to sound as it travels. A burst at 30 kilometers altitude produces a broad ring of modest damage and a startling chorus of booms. A burst at 15 kilometers writes a narrower ring with overpressures that begin to threaten masonry. Direct hearing injury is rare at large distances, yet the startle alone can tip a crowded place into panic. The physics cares nothing for that, yet planning must. If a fragment reaches the ground without complete disruption, then crater mechanics take the stage. The initial hole is not a neat bowl but a transient cavity that opens faster than rock can flow. Material jets upward in a curtain, then falls back as a rim. For compact impacts in soft sedimentary rock, diameter scales roughly with impact energy to a power near 1/3. A 100-meter iron body at 70 kilometers per second would excavate a crater more than a kilometer across, with a curtain of ejecta blanketing many tens of square kilometers. That scale pushes past the boundary between local disaster and regional trauma, with thermal radiation igniting fires and seismic waves rattling structures beyond the crater lip. Such a body is an outlier for a fragment, but worst questions ask the tales of distributions to speak. Water offers different consequences. Ocean absorbs shock generously for small and medium bodies. A 10-meter stone blows a cavity that collapses into choppy waves and a plume. A 50-meter iron piece forces a column that rises like a candle and then falls in steam. The waves born of such events are large locally but fade quickly with distance. To drive a basin scale, tsunami requires a coherent impactor far larger than the typical pieces born of fragmentation. Coastal harbors can still feel meteote tsunamis, waves raised by atmospheric pressure, jumps racing across the surface. Those are annoying to boats and nerve-wracking to night watch crews. Not civilization changing. It is honest to say so. There are precise altitudes where the risk to aviation rises. Flight levels in the lower stratosphere can be brushed by dust and shock. Pilots are trained for bright meteors. The hazard is not heat in the cabin, but secondary effects. Sudden flash can overwhelm night vision on final approach. Ionospheric disturbance can transiently affect high-frequency communications on polar routes. These are managed by rerouting and by warnings that travel faster than rumour. Spacecraft face a different slice of the problem. Molten droplets and small fragments can intersect orbits within minutes of a burst if geometry lines up. Shielded vehicles usually shrug off the drizzle. Sensitive optics may be slewed away from the radiant to avoid streaks that do no damage but ruin exposures. Numbers guide calm. A 10-meter stony fragment at 70 kilometers per second deposits roughly a megaton of energy into the upper atmosphere, with a burst likely above 30 kilometers. Damage on the ground is limited to shattered glass over a broad area and a rain of tiny meteorites that rarely reach city blocks. A 20 to 30 meter strong stone yields a multi-megaton burst between 20 and 30 kilometers. Broken windows turn into damaged facades. Injuries come from glass and falls rather than heat. A 50-meter iron delivers tens to hundreds of megatons at altitudes that bring higher overpressures to the ground. That scale is a nightmare for a dense urban area directly below. Yet the world is wide, and the probability that such a piece arrives on the wrong night, above the wrong grid, is small. Worst is a ruler for readiness, not a prophecy. There is a side effect that turns up in records after bright events. Microbaroms and infrasound bounce around the globe for hours. The atmosphere becomes a bell that has been struck. Arrays built for treaty monitoring, listen, and triangulate. From these signals, analysts reconstruct energy without seeing the fireball at all. The method works in cloud and daylight and over oceans. It is the quiet counterpart to camera networks, and it anchors yield estimates that would otherwise wobble in the noise of eyewitness reports. Fragments that resist complete ablation sometimes survive as stones that can be held. Their fusion crusts are black and smooth. Their interiors sometimes show chondrules or shiny metal flakes. Recovery teams sample them for isotopes that speak of cosmic ray exposure ages and for minerals that tell about parent bodies. Interstellar origins would announce themselves with noble gas ratios or oxygen isotope patterns that sit away from known groups. That kind of forensics would be scientific treasure after a frightful night. It would also calm certain public narratives by replacing speculation with laboratory fact. Mitigation at the minute scale is not interception in space, but posture on the ground. Early warning can come from telescopes that noticed a fragment days before, or from space-based infrared sensors that spot the hot head of an entry while it is still over the horizon. If minutes exist, air traffic can be diverted, sirens can move people away from plate glass, and first responders can prepare for injuries dominated by shards and falls rather than burns. If only seconds exist, advice is as old as thunder. Do not stand at windows to watch the flash. Look away and open your mouth to spare your ears. Wait for the boom before moving. The question asks for the worst that interstellar speed can do with a splinter rather than a mountain. The honest boundary is severe but stops short of global harm. Regional destruction is possible for the larger tail of fragment sizes, especially for strong material and unlucky geometry. Smaller pieces make spectacle and noise and break things that can be repaired. Between those poles lives the space where preparation matters most. Understanding speed, angle, material, and air tells how a night will proceed. That understanding is a way to anchor awe and fear to numbers that do not blink. Air judges every visitor with two quiet verdicts: how much light will be scattered, and how much heat will be moved from where it is to where it is not. A small body that breaks high leaves more chemistry than rubble. The chemistry begins with ablation, where metals and silicates vaporize and then condense into nanometer smoke. Those particles drift in the mesosphere like embers that never cool to solid ground. Iron, magnesium, sodium, and silicon oxides assemble into clusters that clump into tens of nanometers, then hundreds. Each cluster is an efficient scatterer of blue light, and an eager seed for noctilucent clouds in polar summer. The polar sky answers first. Silver veils brighten at the edge of midnight. Cameras record ripples that ride gravity waves. Beauty arrives before consequence. Radiative consequence follows more slowly. Nanoparticles absorb and re-emit infrared, cooling the thin air where they float. Cooling strengthens the temperature contrast across the mesopause. Winds adjust. The circulation that lifts air in the summer polar mesosphere and sinks it in winter grows a little more emphatic. That adjustment modifies how much water vapor reaches the cold shelf where noctilucent clouds form, and it shifts the altitude of layered metal atoms that glow at night. None of this bends weather at the surface. It does leave fingerprints for instruments that can read temperature from emission bands and wind from Doppler shifts. If a planet crosses a dense trail, those fingerprints briefly deepen, then fade. Odd nitrogen is the next ledger entry. Hot fireballs drive shock chemistry that binds nitrogen and oxygen into No and number. Sunlight extends the chain to No, then returns it, creating a catalytic pair that destroys ozone until the sun sets or the compounds are carried away. A single burst draws a thin scar of ozone reduction that stretches with the wind. Many bursts along a path sketch a broader patch. The depletion is not catastrophic. It spans a few percent to perhaps a few tens of percent over a swath measured in hundreds of kilometers and in hours to days. The upper stratosphere and lower mesosphere feel it most. Ultraviolet at the ground hardly notices. The upper air keeps the memory in satellite maps where colors shift slightly toward absence, then recover as transport dilutes the chemistry. If fragments ignite fires on the ground, soot and brown carbon become a different path to the sky. Cities burn hot enough to loft smoke to the upper troposphere. Deep convection can punch some of that load into the lower stratosphere, where residence times extend from months to a year. Black carbon warms the layer in which it floats and cools the surface below by shading. The effect from a handful of urban fires is local and episodic. A chain of urban ignitions along a continent would touch regional temperatures for a season, depressing peak daytime highs, a fraction of a degree and reddening sunsets. The scale that troubles global harvests requires an improbable confluence of many large fires in a short span with strong lofting. That confluence belongs to catastrophe planning for other reasons, not to the ordinary passage of a fast visitor. A more efficient route to global cooling would be sulfate aerosol in the stratosphere. Volcanic eruptions achieve this by injecting sulfur dioxide that oxidizes into sulfuric acid droplets. Bolide impacts can mimic volcanoes if they vaporize sulfate-rich rock. The material must reach the stratosphere and stay there. Small airbursts do neither. A cratering event in an anhydrite basin could. The threshold sits far above the fragment sizes that statistical tales usually deliver. If a rare large body struck such a target, the aerosol optical depth could climb by tenths for months to a couple of years, dimming direct sunlight by 1% or more, and enhancing diffuse light that leaks around leaves. Crops would draw both harm and help from that balance. Cooling would slow growth in marginal seasons, while extra diffuse light could boost canopy photosynthesis under some conditions. These trade-offs are measured after volcanoes. A bolide could repeat them, but only if size and geology both conspire. Twilight tells the story of smaller loads. Even a modest injection of meteoric smoke and dust brightens the belt that follows the sun below the horizon. Purples deepen, greenish bands from oxygen shine more clearly, and a faint glow lingers an hour after sunset. Such changes can be seen after strong meteor showers when the upper atmosphere is seeded more generously than usual. If a single trail rains dense dust for a night, photographs from many longitudes would show similar glows, and sky watchers would report pillars and rays that are rarely seen. The radiative forcing tied to those displays is minuscule. The psychological forcing is not. People behave differently when the familiar sky misbehaves, and behavior is part of the equation whenever risk is counted. Signals through the air feel the particle burden. Satellite-to-ground links that graze the limb-cross layers where electrons and tiny aerosols share space. Scintillation increases as the refractive index fluctuates along the path. The effect is common during solar storms and during strong meteor showers. A short-lived enhancement tied to a dense crossing would push error rates upward for minutes. Systems designed with redundancy ride through such noise. Systems balanced on margins may briefly stumble. Navigation networks are robust at the architectural level, yet individual receivers can show jitter. Aviation routes that rely on polar high-frequency communication also watch these layers. They can shift south to avoid the worst nights with little penalty. Chemistry touches the oceans as well. Nitrates from odd nitrogen eventually return to the surface in rain and snow. The amounts from meteors are small compared to lightning and industry. A sharp shower on a high-latitude sea might deliver a measurable extra pulse of nutrient on a single day. Phytoplankton would use it where water is otherwise clean and light is abundant. The signal would be a faint, temporary greening in chlorophyll maps. In rivers and lakes, deposition would be swamped by watershed inputs, unless the water body sits under a clear, dry sky and away from cities. Worst cases do not bloom from such trickles. Cooling in the upper air has another subtle consequence. When the mesosphere chills, its density falls. Satellites in very low orbit feel slightly reduced drag for days to weeks after a widespread meteoric injection, until the altered thermal structure relaxes. The effect is small next to the drag swings driven by solar ultraviolet variability. It can nevertheless register in precise tracking for CubeSats and for debris near the threshold where re-entry timing is sensitive to density. Operators fold these offsets into their models the way they fold geomagnetic indices, with a minor update rather than a redesign. Eyes near the poles look for more frequent noctilucent cloud sightings after a heavy seeding. Those clouds are climate sentinels, but they are not climate drivers. They respond to water and temperature at about 83 kilometers altitude. They brighten when smoke offers more nuclei. After a dense meteoroid event, observers may count more filaments and brighter veils. The beauty can be exploited for measurement. LiDARs and cameras extract particle sizes from the way those veils scatter color and polarization. That information feeds back into models of sedimentation. The descent of meteoric smoke from the mesosphere to the stratosphere takes months. Along the way, particles grow by coagulation and by sulfuric acid condensation when the air offers it. By the time the particles sit in the lower stratosphere, they are large enough to scatter red light efficiently and to act as a minor mirror to space. The mirror is too small to make winter. It is large enough to paint sunsets. The architecture of the stratosphere decides how long any mirror lasts. Brewer-Dobson circulation carries air upward in the tropics and downward at high latitudes. The quasi-biennial oscillation modulates tropical winds with a period near 2 years, influencing how tracers spread. If a meteoroid event happens when tropical upwelling is strong, smoke spreads poleward more quickly. If it happens during downwelling, layers stack and linger. These patterns matter to those who calibrate radiometers. They matter less to farmers and grid managers. Time smooths the perturbation. The sky returns to baseline while the next dusting from ordinary space drizzle resumes its quiet rule. There exists a threshold that none of these gentle mechanisms cross. Global climate only shifts when radiative forcing is sustained and large. Volcanoes achieve that scale. Great impacts achieve it as rare punctuation marks in the fossil record. Fast fragments and dense trails do not. The worst credible consequence for air and light from a typical interstellar passer is a brief strengthening of noctilucent clouds, a temporary tweak to ozone in the upper layers, a short-lived brightening of twilight, and a handful of operational inconveniences that engineering already knows how to bank around. Even that summary deserves numbers and days attached to it. Instruments can provide them. They will measure aerosol optical depth, map ozone, track winds, and issue concise forecasts that replace rumor with plots. The quiet value in this topic is rehearsal. By practicing how to translate smoke and light into clear guidance, institutions become better at the less frequent but heavier events that nature occasionally assigns. Air is where stories of energy find their endings. Cooling and scattering are its library. Each new visitor adds a page. Some pages are pale, a few are vivid. All are legible to a species that has learned to read the sky. A comet's second soul is electric. One tail is dust, the other is plasma, and the latter answers to fields that stretch from the sun to the edge of darkness. Neutral molecules lifted from the nucleus do not remain neutral for long. Ultraviolet light knocks electrons free. Solar wind protons steal electrons by charge exchange. The newborn ions feel a motional electric field given by the solar wind velocity, crossed with the interplanetary magnetic field, and they are swept away downwind. That sweep carves a narrow, luminous lance of CO+, HO+, and other fragments, a lance that can reach tens of millions of kilometers and that never points where the nucleus is going, only where the star's breath commands. Close in, The flow builds an induced magnetosphere. Plasma piles up around the expanding coma, and a bow shock stands where the wind is first slowed. Field lines drape and wrap, turning the magnetic geometry into a cometary cloak. Within that cloak, collisions are rare, yet momentum is shared by electromagnetic persuasion. Mass loading is the clinical phrase. The solar wind becomes heavy with pickup ions that were born cold and accelerated sideways until they gyrate at hundreds of kilometers per second. Rosetta once drifted inside such weather and saw the shock breathe and wander, the boundary flexing with sunlight and outgassing. Those observations turned textbook sketches into living maps. A tail is not a rail, it breaks. Sector boundaries in the solar magnetic field carry reversals that slide past like unseen walls. When a comet crosses such a boundary, reconnection can cut the tail. For an hour, the far reach is severed. Then a new strand begins to grow, aligned with the fresh field. Coronal mass ejections are rougher hands that can wrench the entire structure, bending it, brightening it, and shredding the plasma sheet into knots. Spacecraft have watched these disconnection events from the safe remove of heliospheric imagers. The frames show a luminous spear that snaps, then regrows, as if the comet exhaled silk into a storm and the silk tore. An ion tail can span Earth's orbit in length, though not in thickness. Widths are measured in tens to hundreds of thousands of kilometers, their cores denser than their faint skirts. Earth is a larger target than it feels like, and the geometry that brings a planet through such a lance is rare but not forbidden. When alignment is right, the magnetosphere becomes the laboratory. Windward monitors would see the usual solar wind gas mixed with water group ions that are not native to the near-Earth environment. Their mass-to-charge signatures would stand out in spectrometers. The bow shock would feel a small change in Mach number because mass loading alters the effective sound speed. The magnetosheath would run turbid with unusual composition. The magnetopores might ripple a little differently as dynamic pressure is spent accelerating heavier ions. Ground consequences depend on fields, not on chemistry. Currents in power grids respond when the interplanetary magnetic field points southward and couples efficiently to Earth's field through reconnection. A cometary tail does not flip that switch. It can, in principle, seed the upstream flow with ions that change the details of how energy is dissipated in the sheath and boundary layers, but the dial that drives geomagnetic storms is still turned by the Sunday. If alignment with a strong solar storm occurred while the planet sat inside a dense tail, ring current chemistry could tilt. Oxygen-rich ions accelerate more readily at some energies and less at others, reshaping the spectrum of particles that drift around Earth and power aurora. The sky would answer with color and texture more than with voltage. Auroral curtains might show unfamiliar emissions superposed on the usual oxygen green and nitrogen red. Faint bands from CO+ or other fragments, noticeable to spectrographs more than to the naked eye. Spacecraft would feel the brush most clearly. Instruments that sniff ions would map a transition from proton-dominated wind to a cocktail of heavy species. Pickup ions gyrate with radii set by their mass and the field strength, and those gyromotions can flood detectors designed to count sparser populations. Surface charging models would be updated to account for altered plasma temperatures and densities in the sheath. Nothing about this implies mechanical harm, but operational envelopes are written by assumptions, and a tail crossing nudges those assumptions enough to merit a careful checklist. Thruster plumes interact with ambient plasma differently when water group ions are common. Radio propagation through the sheath acquires a slightly different refractive index. Small things, measured best by those who live with small things. If proximity to the nucleus were extreme, neutrals could matter too. A vast exosphere of water and carbon monoxide expands with the wind, ionizing on timescales of hours. Should even a thin limb of that exosphere wash over the magnetosphere, dayside ultraviolet glow would brighten faintly at lines associated with resonant scattering from the new species. The geocorona would gain a temporary accent. Such a case would be less a hazard than a gift to instruments that exploit chance to sample worlds at a distance. Neutral gas at 1 astronomical unit is an ocean of almost nothing, but cameras and spectrometers have learned to make almost nothing speak. The magnetotail is Earth's own plume of plasma, stretched away from the Sunday. If a cometary tail overlapped that structure, reconnection could cut and rethread field lines in a way that splices one tail into the other for a time. Bursty bulk flows would carry mixed populations downtail, and substorms might unfold with slightly altered cadence as energy release is modulated by extra mass in the sheets. Ground magnetometers would record signatures nearly identical to ordinary substorms. Only detailed particle composition would tell the story correctly. In that sense, a tail crossing is a lesson in humility. It changes what specialists see without changing what most people feel. Worst thinking asks whether a tail could become a conduit for trouble. Could it act as a wire that funnels a solar storm more efficiently into the magnetosphere, or as a shield that blocks it? The physics says neither. Coupling depends on field orientation, on speed, and on density, integrated over scale sizes much larger than the width of even a generous ion tail. Mass loading can soften shocks and spread boundaries. It does not create power from nowhere, and it does not grant safe passage to flows that were already energetic. The path to blackouts and satellite anomalies remains what it has always been: a southward field for hours, a high-speed stream, a strong pressure pulse. A cometary tail is embroidery on that cloth. Models are ready to test these ideas on the fly. Global magnetohydrodynamic codes can ingest a plume of water group ions at the dayside boundary and compute how the magnetosphere reshapes. Kinetic treatments handle pickup ion physics where gyroradii and gradients are comparable. Assimilation frameworks can merge upstream measurements from monitors like ds-COVA with composition data from magnetospheric missions. Forecast centers that usually publish KP and DEST could, for a day, add a footnote that composition is unusual and that minor effects on satellite drag and surface charging are possible. It would be a scientific holiday more than a civil alert. There is history to anchor the imagination. Earth has crossed ion tails before and noticed only with instruments. Panic once bloomed when a famous tail drifted across the planet, and newspapers sold fear of cyanogen. Yet air remained air, and fields remained fields. That memory is useful in setting tone. The visual artifact of a great tail does not carry the dynamo that powers aurora or the capacitor that discharges into grids. It is the sun and its storms that do those things. A comet adds texture, traces, and an opportunity to watch the magnetosphere learn a new accent. If an interstellar visitor carried an unusually powerful engine of outgassing, the densities in its tail might exceed the ordinary by a modest factor. Even then, dilution over astronomical distances is relentless. The plasma sheet would thicken by small percentages. Pickup ions would color spectra and tweak dispersion relations. No sane forecast would escalate beyond advisory. The practical preparations would be straightforward. Calibrate instruments for heavy ions. Point auroral spectrographs to catch faint bands. Stow sensitive optics on satellites during the hour of densest crossing. Let the power grid watch the sun, not the comet. The reward would be knowledge. A planet could watch in real time as solar wind, heavy ions, and a magnetic bubble negotiated a passing handshake. Satellites would collect a dataset that normally demands a spacecraft to chase a comet for years. The night would answer with a halo slightly richer in lines, the day with plots slightly richer in structure. People on the ground would feel none of it unless they looked up and saw a blade of blue and silver on the horizon at dusk. In the quiet after such a crossing, the magnetosphere would shed the borrowed accent and return to its usual vowels. The tail would drift away with its parent into deeper space. What remained would be a better map of how fields and ions converse, and a better instinct for separating spectacle from risk. In the long arithmetic of worst cases, a comet's plasma gift is therefore a marginal term. It is not the hand that flips the planet's switches. It is a tracer that reveals how those switches work. Gravity keeps its voice low when the mass is small. A visitor of ice and dust may blaze in sunlight and speak loudly in chemistry, yet its pull remains a whisper. Rumor, on the other hand, wanders easily. It imagines tides rising beyond reason, axes tilting, orbits shuddering. The arithmetic refuses those fantasies. A modest nucleus cannot tug a planet any more than a sparrow can tow a ship. Numbers set the scale. Take a compact sphere a kilometre across with density characteristic of porous ice and rock. Such a body weighs on the order of a few trillion kilograms. The Moon weighs about 7 times 10 to the 22nd kilograms. The ratio is roughly 1 part in 10 quadrillion. Gravitational effects scale with mass. A satellite that feels a strong hand from the Moon would not notice a fingertip from a small comet. Tides give the clearest comparison. The differential pull across Earth due to a passing body is approximately 2 times the gravitational constant, times the mass, times Earth's radius divided by the cube of the separation. Suppose separation equals the distance to the Moon. Insert the mass of a 1-kilometer comet, and the calculation returns a tidal acceleration around 3 times 10 to the minus 17 meters per second squared. The lunar tide at the same distance is around 1 times 10 to the minus 6 meters per second squared. The cometary tide is therefore smaller by about 100 billion. Oceans do not stir for 100 billionth of the Moon's pull. Crust does not flex. People do not feel such numbers. Momentum exchange tells a similar story. Even a very close flyby that avoids impact cannot change Earth's motion in a measurable way. A useful yardstick for the speed change imparted to a planet during a near miss is 2 times the gravitational constant times the comet's mass divided by the product of the impact parameter and the approach speed. Choose a grazing distance comparable to Earth's radius and a swift interstellar speed of 30 kilometers per second. The result for Earth is a speed change of the order of 1 billionth of a meter per second. That is smaller than the drift of a snowflake in still air. No clock or orbit solution would notice. Concerns sometimes pivot to satellites. A comet's gravity at 10,000 kilometers is tiny. The acceleration equals the gravitational constant times the mass divided by distance squared. For a 1 trillion kilogram body that is around 1 trillionth of a meter per second squared, integrate over a full day, and the accumulated speed change remains on the order of 1/10 of a micrometer per second. Orbits do not care about such a nudge. Station-keeping burns are larger by many orders of magnitude. The dominant forces in low orbit are atmospheric drag, Earth's oblateness, and tugs from the Moon and Sunday. A passing icy pebble does not join that list. Capture attempts by a planet tell their own tale. To trap a body into bound motion, the system must remove enough energy to take the hyperbola down to an ellipse. In celestial mechanics, that loss usually arrives through 3 body interactions. For example, a pass through the deep gravity well of Jupiter, while simultaneously shedding energy to a moon. The cross-section for such surgical encounters is minuscule. A small visitor can be bent, slowed, and heated by Jupiter. Jupiter cannot be moved by it in any way that matters. The same is true near Earth. Temporary capture into looping geocentric paths is common for rocks the size of chairs. The larger a body gets, the harder it is to trap without friction. Interstellar speeds make the difficulty greater. Space-time curvature offers another angle for the imagination. Einstein taught that mass tells space how to curve, and curved space tells mass how to move. A mountain curves space. A house curves space. A comet curves space. The measure of that curvature near a small nucleus is microscopic. Gravitational redshift near its surface would change frequencies by parts in 10 to the 16. Clocks will not notice. Photons passing a few kilometers from the nucleus would bend by nanoseconds of arc. Telescopes will not notice. Gravitational waves from its motion through the solar field are immeasurable. Relativity keeps its precision and keeps its silence. Microlensing belongs to the same quiet. A compact mass can act as a lens when it passes in front of a distant star, magnifying the star's light by a tiny factor for a short time. The Einstein radius for a 1 trillion kilogram lens at astronomical unit distances is so small that the event would be invisible to present surveys. No glow will announce a gravitational miracle. For visitors this small, light curves trace dust and gas rather than curves in space-time. One might ask about perturbations to fragile structures in space. Could a comet's gravity tip a space elevator, if one existed, or tug clouds of debris into alignment? The elevator lives in theory for now. Debris behavior is governed by collisions, sunlight, and the slow hand of atmospheric drag. Gravity from a small passer cannot rearrange a cluttered shell. It does not herd fragments or clear lanes. If 2 objects happen to be within tens of kilometers of the nucleus during a crossing, They would feel a gentle pull for minutes, then nothing. Such proximities are rare, and the pull is small. This is not a shepherd, it is a passerby. The Sun dominates everything within the planetary family. A comet near one astronomical unit sits deep inside the Sun's Hill sphere. Its own Hill sphere, the radius inside which it could hold onto a moon against solar tides, is tiny. For a trillion-kilogram body at one astronomical unit, the Hill radius is on the order of 100 kilometers. That little volume could trap a wandering pebble for a while. It cannot extend influence across space to touch a planet. The hierarchy of gravity is strict. Large masses claim large neighborhoods. Small masses borrow them briefly and return them without a mark. Could a visitor jostle the orbits of small asteroids or dust bands and seed problems for later years? Encounters that matter require positional coincidence within hundreds of kilometers. The solar system is spacious and bodies are few. When coincidences happen, the usual players are planets. A random hyperbolic traveler contributes far less than the background of mutual tugs that asteroids already share with one another and with Jupiter. The net effect on the dynamical climate is indistinguishable from zero. Occasional fears drift toward axial tilt and rotation rate. Those are set by the distribution of mass within Earth and by the strong torques from the Moon and Sunday. A small external pull provides no lever. Only an impact large enough to rearrange mass inside the planet could adjust tilt or day length in ways that instruments would register. That slides the question from gravity to collisions, from pull to hit. Gravity itself remains a quiet spectator. There is a gentler point worth making. The same modesty that limits danger limits opportunity. A tiny gravity well cannot hold a thick atmosphere, cannot retain geysers for long, cannot shepherd a grand ring. It also cannot wrest satellites from their paths or scrape tides from seas. The visitor is a messenger of other things. It carries chemistry and structure and speed. Those are the parts that demand attention. The pull is an aside. Even the extreme hypotheticals behave. Imagine a dense, multi-kilometer iron body passing just outside the atmosphere. Its mass rises by a factor of 1,000 over the icy pebble case. Tidal effects scale with mass, so the tide rises by 1,000. A tide 100 millionth of the Moon's pull is still a whisper. The gravitational speed change imparted to Earth rises by 1,000 to a trillionth of a meter per second. That is still a whisper. The mathematics refuses melodrama. This restraint is a gift. It allows conversation to stay accurate. When a bright stranger appears, it is natural for fear to search for levers large enough to move continents. Gravity does move continents when supermoons and solar tides lean together, but that choreography is ancient and familiar. A small, fast stranger is not an extra conductor for that symphony. It is an ornament that glints and departs. For completeness, one can look for corner cases. If a visitor flew through the very inner magnetosphere and brushed the geostationary ring, could its pull stretch tethers or perturb station keeping in real time? The answer remains no for practical purposes. Forces from Earth's own non-uniform gravity field, solar radiation pressure, and even thermal re-emission dominate. The comet's contribution would be lost in noise. If a deep space probe passed within tens of kilometers of the nucleus, local gravity would matter for navigation around the nucleus itself, not for anything else. That is a mission design problem, not a planetary hazard. Gravity therefore offers a sober verdict. The small body is interesting for what it carries, not for what it can pull. Oceans will not climb new steps. Orbits will not be rewritten. Power lines will not hum because a distant stone curdled the curvature of space. The worst that gravity can do here is to bend the traveller's own path a little, to guide fragments toward or away from exact lanes, and to lace a trajectory with elegance. That modesty is a relief, and it is also a standard for discourse. When fear speaks loudly, it helps to have a quiet equation that sets the volume. The fear is older than telescopes. If stones travel between suns, could they carry sleepers within, tiny passengers waiting for warmth and water to wake them into appetite? The question has a drama that outpaces the evidence, yet it deserves a careful room where slow thinking replaces legends. Seeds from the dark is a phrase that fits more than myth. It fits spores, cysts, and the stubborn fragments of biochemistry that cling to mineral pores with a patience beyond the usual appetite of life. Begin with the voyage. Interstellar travel is not a sprint measured in years. It is a drift that can last longer than continents have existed. Radiations salt the route with charged particles energetic enough to carve tracks through matter. Ultraviolet light bleaches surface molecules until they break into simpler chains. Thermal cycles shiver rock and ice. Desiccation drives water from niches where chemistry prefers to move. For an organism to outlast such a journey, it must accept long desert and long cold and a rain of energetic particles that shatter DNA and proteins into puzzles. Shielding is the first hope for any passenger. Rock becomes a blanket when thick enough. A few centimeters reduce ultraviolet to a rumor. A meter of stone or compressed ice turns galactic radiation from a killing storm into a slow drizzle that damages but does not instantly sterilize. The depth that brings survival is a negotiation between dose and time. Spores from hardy bacteria can repair double strand breaks in DNA if enough cycles of warmth allow enzymes to work. But time in deep space does not offer such cycles. Without repair, damage collects like dust. Millennia are survivable with comfort. Millions of years become a borderline, and tens of millions push the envelope into a realm where only the most extreme claims approach plausibility. A fragment that left a nursery and wandered for eons would need to be both thick and fortunate to deliver viable passengers to a new warmth. Arrival is the second challenge. Entry at planetary speed is a furnace around any forward-facing surface. Small grains flatten into droplets and fall as tiny glass. Larger stones develop fusion crusts as outer layers ablate. Interiors can survive if size and material cooperate, as meteorites on museum shelves quietly prove. Yet the speeds carried by an interstellar fragment sit at the high end of what air will tolerate before turning stone to vapor. Heat follows pressure, and pressure follows speed squared. A pebble that might survive at ordinary meteoroid speeds becomes a firefly that leaves only smoke at 70 kilometers per second. Survival of intact microenvironments then requires a rock that is large enough to protect a cool core and that arrives with geometry and material strong enough to hold that core together. Such rocks are rare in the fragment trains of brittle comets. Suppose a capsule of micron-thick mineral pockets does reach the ground. The third challenge waits there. Biology is provincial. Viruses recognize specific receptors. Enzymes evolve to fit toys made of familiar sugars and familiar chiralities. Life on Earth uses left-handed amino acids and right-handed sugars. An alien biochemistry may invert that choice, or use a different alphabet entirely for information and structure. A pathogen requires a shared language at the level of cell doors and internal machines. Without such shared language, it becomes a stone tiger with paper teeth. A molecule can still irritate or poison without a receptor, but the grand fear of a new pandemic seeded from the dark is at odds with evolutionary logic. Even within Earth's ecosystems, cross-species jumps are rare and require deep homology. Across separate origins, the odds fall further. There are corner cases that deserve adult attention. A catalytic molecule does not ask for a receptor to cause mischief. A small peptide with the right side chain could bind metal ions in ways that interfere with enzymes common to many forms of life. Abiotic toxins do this daily. Yet a comet does not carry concentrated industrial poisons. It carries dilute organics and ices embedded in a porous matrix. Dilute organics already fall to Earth every day as interplanetary dust and meteoric smoke, and ecosystems metabolize them without drama. A thick layer would be required to cause environmental harm, and no cometary passage can lay such a blanket over continents unless the body is large enough to be a different story entirely. Direct infection aside, there is a quieter scenario. Could genetic fragments from a foreign chemistry act as seeds for recombination or mutation in terrestrial microbes? The machinery for recombination relies on base pairing that demands shared letters. Without that, fragments are broken down as food. Even if letters are shared by coincidence, code tables could be different. Ribosomes might read triplets in a language Earth does not use. The pieces become amino acids, then energy, not messages. Fear sometimes flips the direction. If a spacecraft were sent to visit a fast traveler, could it bring unwanted passengers from Earth that then seed another world? The craft would be sterilized by oils of policy and by heat and clean rooms. Even so, terrestrial microbes find ways to ride on machines. The difference is that a comet's surface is not a garden ready for colonists. It is vacuum, ultraviolet glare, and frost that sublimates under any lamp. Forward contamination in such an environment is more a question for ethics than for ecology. The ethic is simple. Treat every world as if it were already precious in its own terms, and keep human fingerprints off its first pages as much as engineering can manage. Planetary protection protocols exist because questions like these refuse easy endings. Samples are handled in laboratories designed to contain unknowns. Double seals, negative pressure, sterilization lines, and redundant sensors form a ritual that honors both curiosity and caution. The most likely contents of a captured grain from a fast object are minerals, carbon chains, and gases trapped when ice formed at low temperature. The laboratory that opens such a grain opens it under rules that could catch and quarantine the unlikely. The culture that funds such a laboratory needs a calm public that trusts the ritual. Honest explanations are the best instrument for that trust. There remains a philosophical thread. If life can travel, perhaps it already has. Perhaps biology on distant worlds and biology here are one lineage with roots older than this star. That story would be an argument for kinship rather than fear. It would also imply that life is durable to a degree that nothing in present data supports, since the gulfs between stars are long and the radiation between them unforgiving. A milder version of the story is local. Rocks can be thrown from one planet to another within a system by impacts. Viable spores have an easier time surviving such shorter trips and gentler entries. This local panspermia remains an active scientific debate, with reasonable evidence on both sides. Interstellar transport, by contrast, is a colder bet. Another thread suggests deliberate seeding by civilizations older than this one. It is a hypothesis that has occupied imaginations for decades. Testing it requires signatures that rise above coincidence. Capsules designed for endurance would leave materials that chemistry could identify as manufactured. Genomes engineered for message would carry patterns that statistics could separate from natural history. Absence of such signals is not proof of absence, but it is a signal that speculation should keep its humility. In the ledger of risks, directed seeding is a story for fiction until evidence appears in a vial and survives skepticism from the best rooms. In the practical column, the environment after a luminous night holds simple work. Teams collect air filters from aircraft and balloons to count meteoric smoke. Chemists assay rain for nitrates and trace organics. Microbiologists culture samples not because they expect alien colonies, but because science that is worth doing disciplines itself to look, even when it expects to find nothing. Communication teams prepare language that respects fear without feeding it. The sentence everyone wants to hear is short. No hazard to health has been detected. Evidence points to mineral and organic material that matches the sky's usual drizzle, only thicker for a day. Possibility never falls to zero. Life surprises every field that borders it with ingenuity. That is why caution earns its budgets. Yet, when numbers are multiplied honestly, the product does not rise to nightmare. Interstellar time sterilizes. Entry heat cleans. Biochemical diversity raises barriers. The consequent space that remains is narrow and points toward curiosity, not toward quarantine tape around cities. The real danger is that imagination, when left untethered, will fill the vacuum with creatures that do not care about thermodynamics or language. In the long inventory of what a fast visitor can do, biological hazard is a small line near the bottom. It is not absent, but it is thin and annotated with words like improbable, and requires multiple independent luck. Treat it with respect. Test samples with seriousness. Then let wonder return to its first seat at the table. If life is found within a grain from beyond, the first reaction should be awe rather than alarm. A second genesis would expand the room that biology occupies in the mind, and that expansion would dwarf any local worry. Seeds from the dark are an invitation to think about origins, not a reliable script for catastrophe. Uncertainty comes with a heartbeat. Screens glow in control rooms, eyes scan plots, and the room breathes at the pace of new points added to a graph. The object is only a dot to most people, yet the dot carries a rumor that travels faster than light across a network built for attention more than for patience. In that network, fear and wonder share the same bandwidth, and both are amplified by novelty. A species wired to notice rustles in tall grass notices a whisper from the sky with the same reflex. Risk has two halves, consequence and probability. Minds are generous to the first and stingy to the second. Vivid pictures of fire help the imagination, while fractions on a page do not. A number like 1 in a million can feel like either a promise or an omen, depending on how the day has gone. Psychologists have given names to these bends in perception: ambiguity, aversion, availability, anchoring. Names do not dissolve them. Language must work around them. It must be concrete, repeatable, and timed before rumor sets its hooks. If a corridor of possibility narrows at 2:15 UTC on a given date, that timestamp is a kindness. Clocks pin emotion to something that can be checked. Institutions build habits to guard against the tide. A warning network publishes cadence rules, daily updates while uncertainty is wide, twice daily when geometry tightens, hourly if a threshold is crossed. Thresholds are agreed in advance, not invented at the podium. Each update carries the same structure, to keep attention focused on the change rather than the style. A figure shows position, a figure shows probability contours, a figure shows consequences if a fragment arrives. The same color map, the same units, the same placement, every time. It looks dull to those who want drama. Dullness is a virtue when stakes are real. Markets listen with their own antennas. Satellite operators read between lines for hints about dust that could raise anomaly rates. Reinsurers watch for language that may imply regional risk. Traders hunt for supply chains that might blink if communications hiccup or if launch schedules pause. The signal can be faint, yet price is sensitive to whispers. History teaches to expect small spikes in demand for satellite phones and generators when headlines turn dark. Most of this settles as soon as a probability shrinks below a line that professionals trust. Managing those lines is part of stewardship. Move them too often and credibility frays. Move them too late and preparation falters. Rumor blooms in the gaps. A screenshot of an internal plot leaps across timelines, stripped of labels. An old image is rebadged as current. Anonymous accounts claim insider knowledge of impacts, evacuations, secret bunkers. The multiplication factor of a lie can be measured not in epidemiological R numbers, but in retweet half-lives and cascade depths. The cure has two ingredients: pre-bunking and speed. Before falsehoods appear, a public note explains what real products look like, which addresses host them, and what words will never be used. When falsehoods appear anyway, authoritative accounts reply with links to the current, signed bulletin. Silence is not golden during rumor. It is gasoline. Education changes the baseline slowly but lastingly. A school that teaches what a probability cone is, what a minimum distance means, how small forces make large differences over long times, produces adults who will not panic at the first plot they see in a feed. Short animations help more than essays. One map that shows a corridor shrinking as data arrive teaches the eye to wait for convergence. Curiosity is armor when it is fed with simple tools. Public dashboards built by agencies and universities, open to anyone, become anchors in storms of commentary. Decision theory sneaks from classrooms into meetings where budgets live. Options are weighed with regret in mind. If a false alarm leads to prudent pauses that cost little and teach much, it is cheap tuition. If a late alarm leaves a city unprepared for shattering glass, it is an expensive lesson. The value of information becomes a number tied to a time, because another night of observation halves error bars, which halves the area that must be warned, which halves the cost of readiness. A calm sentence can carry this math. One more dawn brings clarity worth the price of waiting. Politics does not sleep through such nights. Leaders ask whether a statement will calm or kindle. Advisors show drafts that begin with certainty and place theory in a later paragraph. Partisans look for blame or credit. The wise response avoids victory language and keeps to the ledger: what is known, what is unknown, what will be known next, and when the next update will arrive. Press conferences favor metaphors that do not lie. A corridor is a corridor, not a bullseye. A passing object is a traveller, not a weapon. The tone is set by verbs that are slow and clear. Ethics tick through the background like a metronome. Data belong to the public when consequence touches the public. Proprietary periods that serve science in quiet times dissolve during possible hazard. Credit remains, pride remains, but access opens. There are exceptions for security, yet those exceptions are narrow. Trust in institutions is worth more than any short-term discomfort that comes from showing work in real time. If a forecast changes overnight, the Morning Note says so plainly and explains why. No one is scolded for asking. Every question receives a link to a resource that respects the questioner. Preparation lives in lists. Hospitals check generators. Schools test intercoms. Airports brief crews about bright events and sonic booms. Pilots are reminded not to stare at flashes on approach. Utility operators verify that alarms are not pegged by unusual ionospheric noise if a dust stream arrives. City offices review simple messages that tell people to keep clear of windows during a bright sky event. None of these steps assumes catastrophe. They assume a night that might be louder than usual. The exercise is the point. Practice accrues interest even if the night passes quietly. Media shape the shared picture. A long lens photograph of a bright tail at dusk is a gift. It should be captioned with scale, dates, and where to look, not with breathless adjectives. Infographics thrive when they admit uncertainty. A slider that lets a viewer drag a time bar and watch the predicted path tighten is better than a still image that freezes a guess. Journalists who enjoy science can teach colleagues how to avoid the trap of superlatives. Words like unprecedented and doomsday are disfavored in rooms where engineers work. The event is the story. The superlatives are noise. There is a smaller, more private economy at work too. Families choose whether to delay a trip by a day. Schools decide whether to take students outside to watch the sky together. Communities arrange a night of telescopes in a park. The act of looking transforms dread into participation. A child who watches a meteor trail across the field of view learns that the world is larger and more interesting than fear suggested. That memory is a form of resilience that policy cannot buy. Global coordination translates statements across languages and cultures. A sentence that lands well in one language may mislead in another, not because of grammar, but because of metaphor. The word safe carries different thresholds in different places. Clear writing avoids it and chooses precise quantities instead. Distances in thousands of kilometers, speeds in kilometers per second, times of closest approach within the local day, with both UTC and local given. Accessibility matters. Alt text for plots, captions for videos, transcripts for briefings, large fonts for mobile screens. These details feel small until a night arrives when millions look at the same page. When the calendar flips to the day of closest pass, a planetary pulse can be felt in traffic maps and in the silence between sentences on trains. The species is good at collective suspense. It has watched eclipses and landings and storms. It can watch this. If the corridor shrinks far from danger, relief flows through systems that were braced and can now relax. If a meteor storm begins, a different energy arrives, one of delight moderated by precaution. If a fragment surprises, the systems that trained for broken glass open their doors. In the postscript that follows, institutions take their own pulse. What messages were late? Which graphics confused? Where rumour beat truth to the street? A report lists corrections, assigns them to names, and puts dates beside each fix. The work is not glamorous, it builds muscle. Risk communication is not a stunt. It is a craft built from empathy and iteration. The sky will offer other tests. People will bring their own weather to each one. Calm, clear language is the constant that threads through all of it. Uncertainty will always be a companion. It is not an enemy. It is the space in which humility breathes. And humility is the clean air that lets science and policy share a room. The beating heart remains the same. Look carefully, speak carefully, decide carefully. A world that practices those three verbs during quiet seasons will find that even the worst questions feel less like cliffs and more like roads with guardrails and mile markers, lit by a patient moon. A planet learns by three crafts that complement one another like instruments in a slow quartet. Eyes gather light across colors. Ears send radio pulses and listen for their own echoes. Shadows reveal profiles when a distant star is briefly erased. Together, they turn a moving point into a body with spin, texture, jets, and rules. The first craft begins with non-sidereal tracking, a quiet trick that moves a telescope at the object's rate rather than at the sky's trailing loss. Falls away, speckled noise smooths, and faint structure rises. Large mirrors collect photons in the optical and near-infrared, while smaller, faster survey cameras stack short exposures with synthetic tracking, shifting frames by predicted motion before adding them. An object that hides in a single picture appears when 100 pictures are aligned and summed. Adaptive optics steadies images by measuring the blur on a guide star and correcting mirrors hundreds of times each second. On good nights, jets can be seen as fans or spirals, their rotation imprinted as corkscrew patterns that repeat with the nucleus period. Spectrographs split the light into signatures that name molecules and grains. Long slits sample along the tail to map chemistry as a function of distance from the source. Integral field units place a grid of tiny spectrometers across the coma, yielding a three-dimensional data cube with two spatial axes and wavelength. From such cubes come production rates for water, carbon monoxide, and carbon dioxide, limits on rarer species, and maps of where activity is strongest. Spectropolarimeters measure how scattered sunlight is polarized as a function of phase angle, which converts to grain size and porosity. Neutral colors with a gentle blue tilt point to fragile, fluffy aggregates. Red slopes with broad absorptions speak of complex organics and radiation-hardened crusts. Thermal eyes in space complete the view. Mid-infrared cameras see the nucleus and dust as heat rather than reflection. A thermal model converts flux at several wavelengths into an effective size and into a beaming parameter that encodes surface roughness. Combine size with the way sunlight accelerates the object through asymmetric outgassing, and a mass appears. Combine mass with volume, and a bulk density follows. Each step carries bars of uncertainty, yet the arithmetic closes on values that tell whether the body is a loose foam or a compact stone. Millimeter arrays can add constraints by detecting rotational lines from CO and HCN, turning points of brightness into column densities along the line of sight. Light curves, recorded with minute cadence, chart rotation. A simple sign hints at a single elongated body, turning with a steady period. Complex waveforms betray tumbling, or a bilobed form, or surface patches that flash when frost and stone trade places in sunlight. Period changes over days announce torque from jets. Phase curves, the way brightness evolves with the angle between sun, object, and observer, reveal surface texture through the opposition effect. A gentle surge near zero phase means fine regolith. A muted surge suggests larger grains or consolidated crust. The second craft relies on a radar that speaks and waits for reply. The principle is old and the equations unforgiving. Signal strength scales with the fourth power of distance in the denominator, so opportunity comes only when geometry is friendly. If the pass is close enough, a long wavelength transmitter illuminates the body while a separate dish listens. Delay Doppler images reconstruct shape by measuring echoes as a function of frequency shift and travel time. Range rate gives velocity along the line of sight within millimeters per second. Delay resolves distance in bins as small as a handful of meters when power allows. Even a blurred radar silhouette can fix size, constrain, spin, and detect companions that light would confuse with jets. Bistatic tricks help when transmit and receive sit in different places. One dish speaks at S-band or X-band, a second listens from far away to catch specular glints and broaden the baseline for delay estimation. Speckle tracking compares the fine, grainy structure of radar echoes at two stations to deduce rotation pole orientation. The loss of a great transmitter has made these experiments rarer, yet the craft persists with creativity, stealing signal to noise from longer integrations and from careful scheduling at the moment of closest range. When range is too great for radar, radio astronomy still helps. Hydroxyl at 18 centimeters is born when sunlight splits water, and its lines can be amplified by population inversions in expanding gas. A detection of these lines yields a water production rate directly, even when optical spectra are faint. Carbon monoxide at millimeter wavelengths is another beacon. A narrow line drifting in frequency with the object's motion allows refined velocity and verification of outgassing when optics struggle with glare or weather. The third craft is the reading of shadows. A star of known position and size sits beyond the moving body. For a second or less, the star winks. Telescopes spread across a continent record light at hundreds of frames per second, while precise clocks stamp each frame. Each station measures a chord across the silhouette. Stack the chords, and a shape appears. The Fresnel scale, roughly 200 meters for visible light at 1 astronomical unit, sets the sharpness of edges in the light curve. Starlight that fades and returns with a gentle slope rather than a step signals a coma. A central flash near perfect alignment hints at a tenuous, extended atmosphere. Subtle pre-dips or post-dips can betray rings or jets of large particles. Occultations regularly surprise, revealing arcs around small bodies that no camera had seen. The same method can find tiny companions when a second, shallow blink crosses a subset of stations. Prediction is the art that makes shadows useful. Orbits must be propagated with errors intact. Star positions must be precise to milliarc seconds. Gaia catalogues provide the scaffolding. Software computes a path on Earth where the shadow will fall. Then observers drive to that line with portable telescopes and high-speed cameras. Success yields size to within a kilometer, spin state when chords change with time, and constraints on activity when the light curve around the disappearance shows soft edges or color dependence. A single successful event can outperform months of imaging for geometry. Sensor fusion ties the crafts together. Astrometry from images tightens the path. Occultations fix size. Thermal flux bounds albedo. Radar, if available, nails spin and shape. Spectra and radio lines quantify gas. Polarization tells dust. Light curves reveal torque. Feed all of it to a model that allows jets at defined latitudes and longitudes. Add thermal inertia, and let it evolve across a rotation and around perihelion. The model predicts not only where the body will be, but how it will push itself while it is there. That prediction feeds both curiosity and caution. If mass loss will peak at a certain hour, satellites can be slewed and instruments prepped. If a potential occultation path crosses an ocean, aircraft with stabilized cameras can be sent to float under the star. Citizens carry part of the weight. A DSLR on a tracker can measure a light curve with surprising precision when enough frames are stacked. All sky cameras catch meteors from dust sheets that pass minutes after the nucleus. Amateur telescopes, with sensitive video record occultations that professional facilities miss due to clouds. Apps distribute coordinates, finder charts, and timing protocols in plain language. Data land in public repositories where standard formats let researchers merge hundreds of small contributions into a coherent map. Heliophysics missions add context few ground telescopes can supply. Coronagraphs see dust and plasma near the sun when Earth-based eyes are blind to glare. Wide-field heliospheric imagers watch tails bend and break under solar wind pressure and field reversals. Magnetometers sample upstream conditions before a possible tail crossing. These instruments are not pointed at comets by default, yet they often catch them. The data complete the picture by tying local behavior to space weather. Every measurement has rhythm. Surveys sweep, deep mirrors stare, radar chirps, cameras blink stars into absence. The choreography is deliberate because time is precious. Short residence in the inner system demands checklists that work. There are windows for blue light and windows for heat, for spectra and for polarimetry, for occultations and for radar. The calendar fills with slots measured in minutes, each owned by a team that knows exactly what it will do with them. What emerges at the end is not a portrait in oil, but a layered atlas. One layer shows the nucleus as a rough shape with a period and a pole. Another shows the coma, its jets and grains and colors. A third overlays chemistry. A fourth heat. A fifth the way momentum leaks into space and nudges the path. The atlas is enough to answer practical questions with numbers. How bright and how long if it sheds dust. How strong and how frequent if torque grows. How narrow and how late if fragments form. The art of eyes, ears, and shadows turns a visitor from a rumor into a measured presence. And the measurement is the difference between anxiety and understanding. Choice arrives as a triad: outrun for a fast flyby, rendezvous to match its pace, redirect if its path trespasses where lives and cities live. Each choice is a different grammar for the same sentence. Reach a small target that refuses to slow down. Outrun begins with geometry. A vehicle sitting near the inner system can dive sunward for speed, bend its path around the star, and exit along a vector that intercepts the traveler. The dive turns sunlight into velocity through the Oberth effect, a maneuver where thrust at highest speed buys the largest dividend. Heat shields shoulder the burden while engines push. Chemical stages deliver brute impulse in minutes. Solar electric systems add continuous thrust over months, their ion plumes writing faint calligraphy that slowly rotates the trajectory into place. Jupiter offers gravity for those who have time, trading distance for a slingshot that deepens the dive and steepens the outbound leg. None of this is theory alone. Trajectories are found by solvers that juggle planetary positions and engine limits, and declare launch windows by the day and hour. An outrunning flyby takes instruments that can drink data in milliseconds. Cameras must expose in a heartbeat and still resolve vents and ledges. Spectrometers must read bright, rapidly changing lines without saturating. Dust analyzers are tuned to impact ionization, so that a grain shattering on a metal target becomes a signature of its chemistry. Magnetometers and plasma packages map the wind around the body as the spacecraft punches through its coma. One trick multiplies science at speed. A small impactor can be dropped ahead of closest approach to strike the surface and lift a plume. The chaser flies through the plume and samples gases and grains with better count rates than passive sniffing would allow. Aerogel collectors catch larger fragments without turning them into vapor, though the capture path must be thick and patient to slow pieces born at tens of kilometers per second. Rendezvous is the deeper ambition. Matching velocity with a visitor from outside is a sum of many burns and many gifts from gravity. Nuclear thermal propulsion promises high thrust with better efficiency than chemical engines can offer, raising hopes that a vehicle could brake beside the target and drift in formation for weeks. Nuclear electric systems would trade thrust for patience, spiraling outward with xenon or krypton and trimming relative speed at the end. Beamed sails haunt whiteboards, square kilometers of film pushed by light from the ground or from orbit, but they demand infrastructure that exists for concept art more than for launch manifests. Even with the best engines contemplated for near futures, Rendezvous tends to belong to early warning. A vehicle built years in advance and stored at a vantage point can sprint when a messenger appears, rather than begging factories to start the clock after discovery. Waiting is therefore an enabling strategy. A sentry can sit where gravity and sunlight balance gently, its systems asleep, its tanks full. When a target is announced, the sentry wakes and burns. The architecture is modular. A main bus with navigation and high power, two daughters that separate near the encounter and take different sides of the nucleus, a cloud of chipsats that taste dust and field from many cords through the coma. Redundancy is a survival trait. When a single mispointed valve or an unlucky grain could turn a lone probe into a silent sculpture. Multiple vehicles distribute risk and let measurements cross-check each other. Redirect is the part of the conversation that carries weight. If a corridor narrows and an impact cannot be dismissed, what can be done at interstellar speed? Kinetic impactors can alter paths when months or years remain before encounter, but their leverage fades as warning shrinks. A push delivered when the target is far from the planet multiplies over distance into safety. A push delivered late barely moves the line on a map. Standoff nuclear energy can vaporize a veneer and create a jet of expanding gas that acts like a thruster. But the ethics and treaties that govern nuclear use in near space are strict for good reason. Fragmentation is a fear, since many small pieces may spread hazard rather than erase it. Ablation by focused light, either from space-based lasers or from sunlight concentrated by mirrors, writes momentum into gas flow without touching the nucleus, yet the power and aiming stability required are far from present fleets. Mass drivers attached to the surface promise steady thrust by throwing stones backward, but they demand landing under conditions no one can promise. The civil argument that surrounds redirect is as important as the engineering. Authority must be shared across borders because a miss for one region can be a hit for another if timing and aim are poor. The legal framework binds action to responsibility. If a deflection attempt creates fragments that injure a third party, the path to compensation must be clear before the attempt begins. Transparency becomes a safety device. Simulations, assumptions, and predicted corridors must be shown in public, not summarized. Consent is not a slogan but a protocol when a species acts on behalf of itself. Speed complicates ethics further. At 70 kilometers per second, even small interventions are violent. A kinetic impact that would be gentle in another context becomes a flash that excavates and sprays. A standoff burst that would peel a few centimeters elsewhere can peel meters here. Decision makers must live inside exact estimates rather than intuition. Physics is the arbiter. The tone in the room should match the math. Sample return tempts with treasure and risk. A hypervelocity collector can catch grains that cross a flight path and then seal them in a canister that returns through atmosphere with a blunt cone and a parachute. The grains will be shocked and cracked, yet molecules will survive that tell temperature and chemistry. A second strategy uses a dart to bite into the surface and throw material into a trailing capsule. Both require exquisite timing and approach control. Both add mass and complexity. Both face the discipline of re-entry corridors and recovery in the field. The reward is high, because a milligram of novel ice and dust can occupy laboratories for years and answer questions that remote sensing cannot resolve. Swarm tactics change odds. A flock of small probes rides one launch and fans out along the predicted intercept line. Each carries a narrow instrument set. Some aim for plasma, some for dust, some for imaging. A loss rate that would doom a monolithic mission becomes survivable. Small vehicles can fly closer to the nucleus because loss of one does not end the enterprise. Communication protocols are simple and robust, using fixed schedules and store, and forward schemes that do not rely on a fragile real-time link at closest approach. Navigation is the quiet hero of all three strategies. Optical guidance locks onto a moving dot against a frame of stars and walks burns toward proximity. Autonomous systems make micro-decisions faster than light time allows, correcting for jets and flashes the way a pilot rides turbulence. Ranging and Doppler dovetail with optical cues to keep the corridor tight. Even a flyby at a few kilometers per second benefits, when prediction errors shrink from tens of kilometers to hundreds of meters. A rendezvous cannot survive without autonomy that treats a spinning, venting, irregular body as a partner in a dance. Einstein lingers in the mathematics of gravity assists, and Hawking lingers in the courage to ask whether dramatic tools should ever be used to alter a cosmic event. Their names belong in the room to remind everyone that big ideas and careful proofs are different virtues that must travel together. A plan without proof is theatre. Proof without a plan is a paper with no door to the world. Training earns as much credit as thrust. Digital twins of vehicles and targets run in simulators with noise that mimics jitter, sensor glare, and the false accelerations that vents can impose. Teams rehearse handovers between navigation, propulsion, and science with clocks that refuse mercy. Ground systems practice sharing antennas with missions already in flight, since deep space networks are crowded and a sprinting probe will not wait for a gap. Supply chains for propellant, batteries, and thermal protection are exercised on short notice, so that promises made by dynamics can be kept by factories. If the night is quiet and redirect is never asked for, the investments still pay. A sentry catches another comet, or an asteroid that wanders close. Swarmcraft find work near planets, mapping moons from many chords. Fast flyby techniques become standard tools for objects that do not come from afar, but still hurry. The discipline built for worst cases becomes muscle for ordinary science. Agency statements that name the three choices should be brief and stern. Outrun for reconnaissance. Rendezvous if time and engines allow. Redirect only under clear, measured threat with international consent and full disclosure of method. That ladder keeps ambition from jumping steps. It keeps imagination in the service of prudence. It also keeps the species honest about what it can do this decade, not the next. The visitor travels on whether anyone moves, The question is whether a world chooses to meet it as a spectator or as a careful host. Engines, sails, and ethics are the instruments of that choice. They hum differently, but together they can make a sound that is both brave and disciplined. Before engines move, equations travel. A visitor that will never slow for long interviews must be rehearsed inside silicon. So a planet builds a theatre of models and lets a cold actor walk across its light. The stage is divided into chambers. In one, gravity writes curving lines through a clean vacuum. In another, gas molecules strike, stick, and fly. Farther in, dust learns to carry charge and listen to fields. Down a corridor, light scatters through grains and returns as colour. Each chamber has its own craft, and doors between them remain open, so that momentum, heat, and chemistry can pass. The simplest room is not simple at all. Gravity is solved by integrators that honour energy and phase space. Symplectic schemes carry orbits for months without letting errors grow into fiction. High-order adaptive solvers step small where curvature is sharp and stride where it is smooth. Planetary positions arrive from ephemerides that account for relativity and the slight lopsidedness of the star. Into this ballet goes a swarm of virtual clones, each drawn from the cloud of orbital covariance. The clones move as a family, and their spread gives probability weight to each future hour. The same tools deliver a map on the B-plane, a perpendicular screen where one can paint ellipses of arrival and see at a glance which ellipses never touch the point labelled Earth. Gas needs a different script. The flow near a vent is too thin for the equations of a smooth fluid to hold, yet too crowded for particles to ignore one another. Direct simulation Monte Carlo becomes the language, each pseudo-molecule hopping, colliding, and exchanging energy according to cross-sections measured in laboratories. A hollow neck or deep pit collimates the gas into a sheet that turns into a cone as pressure falls. Composition matters. Carbon monoxide leaves faster than water at the same temperature, so the plume is colder and wider if that volatile rules. The gas then entrains dust, so a coupling term pushes grains according to size, density, and shape. Where gas falls below a threshold, grains coast. Dust dynamics asks for its own law of balance. A single parameter, the ratio of radiation pressure to gravity, can describe the first cut, but real grains are not perfect spheres. Needles and fluffy clusters present area without mass and charge without symmetry. The Lorentz force bends the path of the smallest pieces around a field that spirals from the sundae. A hybrid code carries both influences, drifting larger clasts in Keplerian arcs, while letting submicron motes play along magnetic shells. Time-dependent solar wind is added from measurements, so the model can rehearse a disconnection event when a sector boundary sweeps by. Light ties the chambers together because it both heats and reveals. A thermophysical model solves conduction into the first centimeters, allowing for porosity, latent heat, and shadowing by roughness. It predicts where a crust will sinter, where frost will migrate, and which longitudes will sing. The predicted temperature then feeds radiative transfer for brightness and color. Dust scattering is treated with Mie theory for spheres, and with discrete dipole approximations for odd shapes. Spectral lines from gas are ray-traced through the coma with absorption and emission, so synthetic spectra look like something a telescope might actually record. When synthetic spectra match the sky, confidence rises that the interior calculation is not lying. Stress and fracture are given a chamber because stones break. Finite element meshes hold tensile strength and cohesion in small cells. Thermal gradients from the thermophysical room strain the mesh. Spin adds centrifugal load. Tidal terms can be added even when weak, since near a star they help existing cracks lengthen. If stress exceeds a failure criterion, cells disconnect and become fragments that inherit motion, then pass through the gas and dust rooms as new sources. Smooth particle hydrodynamics is used where breakage becomes flow, because rubble does not keep the neat boundaries a mesh prefers. Fields receive a hall with high ceilings. Magnetohydrodynamics treats the coma as a mass-loading obstacle inside a wind. Codes that usually draw planetary magnetospheres are adapted to small, temporary magnetospheres around a plume. The draped field, bow shock, and pickup ions appear on screen. At the interface, kinetic models step in for gyromotions that are too large for fluids to track. The result is a plasma wake that can be compared with in situ data if a probe gets lucky, or with heliospheric images if a tail stretches across the image's gaze. The rooms pass messages through a governor that mines uncertainty. Parameter spaces are large and data are sparse, so Bayesian inference watches each output and challenges it. Prior ranges encode laboratory results for sublimation and tensile strength. Likelihoods measure how cruelly a given set of parameters deviates from the night spectra, images, and astrometry. Markov chains walk through this space until the posteriors settle. Ensemble Kalman filters then ingest fresh measurements and slide the entire state to meet them, shrinking variance as real photons arrive. Posterior predictive checks create fake universes with the chosen parameters, then ask whether those universes tend to draw the same pictures as the sky. Speed makes this theatre sweat. High-performance clusters run the outer loops, while graphics processors accelerate particle pushes and radiative kernels. A single pass through the whole building might take hours if every door is open, which is too slow when a window for radar or occultation will close in minutes. So the architecture is tiered. A fast lane uses reduced models, perhaps a Marsden-style non-gravitational acceleration law for orbit fitting, a Hazer-Coma for gas, and a single-parameter dust law. A slow lane runs the full fusion overnight. When fast and slow disagree beyond agreed thresholds, the team knows where ignorance hides. Validation is not left to charisma. Benchmarks with test problems are baked in. The gravity room repeats the long dance of known comets around a star and checks for secular drift. The gas room recreates jets, observed at a previous target, recovers mass flow with intolerance, and reproduces the width of narrow features. The dust room predicts a famous meteor storm from a known release and earns its license by hitting the hour within minutes. The field hall runs a textbook solar wind, drapes a field across a sphere, and compares with heritage results. Radiative transfer reproduces the reflectance of a powdered basalt bed and the phase function of laboratory soot. Without this humility, the theatre becomes a mirror. Scenarios are rehearsed with a purpose. A script labelled brittle nucleus is fired, cracks form, and 5 fragments peel away with meter-per-second offsets. The gravity room spreads them along the track. The dust room releases a burst of needle-rich grains and maps a fan that will cross geostationary altitudes in 3 days. The covariance manager samples that fan and publishes probabilities by hour. Operators of satellites receive a file that their own tools can digest. A different script, labelled CO-rich jets at high latitude, produces a transverse push that shifts a close approach by hours. Astrometry is requested during a specific window to confirm or dismiss the push. These are not stories told to frighten. They are drills written in code. Hawking once wrote that the universe is under no obligation to be interesting, then spent a life showing that it often is. Einstein left an equation that most days is gentle and precise about how masses move. Both voices echo in this theatre. Curvature guides the path, quantum helps set the way light and atoms talk, and everything else sits between those guides, where geometry and heat argue. The models are a means to listen to that argument without shouting over it. Transparency keeps the audience sane. The parameters used for each run are posted beside the plots. The priors are named, the datasets that tuned them are linked. When the code fails on a corner case, a red stamp notes it. Open repositories carry scripts that will reproduce today's figures next winter. Review lives in public issues, not on a drive under someone's desk. The point is not to embarrass errors, but to keep confidence from resting on charm. There is a softer chamber where words are written. Forecasts are translated from units that engineers love into diagrams that people can hold in a glance. A cone of dust crossing orbital shells becomes a clock face for a city. A posterior on minimum distance appears as a bar that shrinks with each night. A footnote states the assumptions in 2 sentences. This room is part of the model as surely as any solver, because a prediction that cannot be carried by voice will never reach those who need to choose. At a certain point, the digital twin of a traveller feels like a body with preferences. It spins this way, vents that way, fractures at those loads, warms and cools with those rhythms. The twin never claims to be the truth. It is a hypothesis that breathes in numbers, waiting for the sky to praise or correct it. When the night yields a better spectrum, the twin shifts. When a light curve shows torque, the twin admits a vent was misplaced. When a passing gust from the sun cuts the tail and the images agree, the field hall raises a small cheer. In the end, simulating the unfamiliar is not a bet on prophecy. It is a practice in humility that moves the boundary between unknown and unknowable by a little each hour. The worst outcomes are not banished by code, only named with finer ink. The best outcomes, the ones where a world watches a bright arc that harms nothing and teaches much, are better appreciated when the atlas of possibilities was drawn with care. The theatre closes its doors each dawn and saves its state. The actor continues on, indifferent, and the audience returns each night wiser by a few pixels and a few lines of text. The window narrows in 3 ways at once. Light geometry squeezes as the target sinks toward glare. Instruments face their last clean angles before twilight swallows them, and calendars bleed away the hours when choices still change outcomes. What begins as a generous canvas of options becomes an aperture that asks for a single exposure. The world does not stand still for this. Launch pads have other clients, antennas carry other voices, cities run on schedules that do not know, the sky is writing a deadline. The art now is triage without panic. Observation is the first arena where the opening tightens. Solar elongation shrinks until a bright wedge near the sun erases faint structure. Large mirrors on mountaintops consult tables that tell when the object will sit above air mass limits, when the moon will be elsewhere, when weather will cooperate. A last sequence of astrometric frames must be captured to pin down timing by seconds rather than minutes. If a hemisphere loses access, the other takes watch with longitudes that deliver continuity. Redundancy becomes an instrument in its own right. 2 medium telescopes in clear air can outperform 1 giant mirror caught under a wet front, and planners stack slots like dominoes across continents to hedge against clouds that do not read forecasts. Radar offers a second but stricter window. Signal strength falls with the 4th power of distance, so there is a narrow arc where an echo can outrun noise. That arc may last hours, not days. To seize it, deep space antennas are rebooked and transmitters warmed. The target's range rate must lie within receiver filters. Speckle patterns from the rough surface need a baseline wide enough to separate rotation from glint. A decision to try must be made before confidence is total, since travel time to the correct pointing position can rival the length of the usable pass. Success shrinks positional uncertainty by orders of magnitude. Failure still teaches by closing doors that speculation had left ajar. Shadows on stars present their own deadline. An occultation path creeps across the ground at hundreds of meters per second. Teams tow trailers, set up cameras, and sync clocks with disciplined obsessiveness in places where a slip by a minute would miss the blink entirely. Forecast lines are updated by midnight, then again at dawn. By the afternoon of the event, vans are already parked along county roads that line up with the latest path. Weather apps are refreshed with a frequency that betrays nerves. A successful chord gives size without ambiguity and can reveal jets or a faint envelope in the soft edges of the light curve. Misses teach how good the orbit really is. Either way, once the star is behind the horizon, that line in the ledger is inked forever. Data feeding models confront their own clock. Parameters that drift slowly for weeks can jump when a fit tips from one local minimum to another as new points arrive. To protect against last-minute leaps, analysts set freeze times after which changes require consensus from multiple independent pipelines. A final fit produces a trajectory with uncertainties that are honestly earned. Those numbers propagate into every downstream map, from meteor forecasts to satellite risk estimate. The discipline here is to resist the urge to tinker when the window has already narrowed to hours. A late tweak may feel like caution and act like noise. Operators of spacecraft navigate a schedule that feels like breathing against a closed throat. If a dust fan might cross geostationary altitudes, vehicles there rehearse a role that presents armor instead of glass. The role must fit around power and thermal needs, so engineers model sunlight angles with minute resolution. Communication constellations in medium orbit prepare to accept a slightly higher rate of single-event upsets then test uplink channels that can recover nodes without human intervention. Earth-observing fleets plan to shutter optics during the crossing, then open on a cadence that catches the afterglow if meteoric smoke brightens layers where their filters can see. Each maneuver has a cut-off time that precedes the projected crossing by a margin. No one dares to steal for a last data point. If an intercept mission sits on the pad or at a staging orbit, its clock is harsher. Launch windows bound possibilities by celestial mechanics and propulsion limits. An instant too late can cost a kilometer per second of missing speed that no extra propellant can repay. Teams carry checklists that split decisions into green, yellow, and red. A green becomes go by default, unless a sensor says no. A yellow asks for a deliberate meeting that ends in minutes, not hours. A red aborts without shame. This hierarchy protects against the seduction of heroics. Precision, not bravado, is the virtue in the company of fast stone. Decision calculus changes flavor as the window closes. Early on, small chances of large consequences justify wide preparation. Later, improved probabilities shrink the footprint of action. Hospitals that stood ready for broken glass stand down or stay at ease. Airports that briefed pilots about sudden flashes on final keep the briefings but avoid rerouting. Satellite operators who had blocked hours for protective attitudes trim the block to minutes. The value of information becomes explicit. A single extra night of astrometry might cut warning regions by half. If so, that night is more valuable than any press conference. And the press conference should wait until after its photons arrive. Language must converge as quickly as numbers. Public bulletins stabilize phrasing and placement so that the eye knows where to look for the only changes that matter. The headline carries time in UTC and in local time for multiple cities. The first figure shows distance and timing measured the same way each cycle. The second is a map where the scale never moves. The third is a simple action card, one for general audiences, one for aircraft crews, one for satellite controllers. This consistency lowers the mental cost of staying informed and keeps rumour from filling gaps with improvisation. Institutions also decide what not to do. Evacuations for a shower of light are theatre and are never considered. Sheltering advisories for plate glass are warranted only if a strong entry is plausible inside clear tracks. Stockpiling for grid events is futile, because any coupling to power systems comes from the sun, not from the visitor, and the sun's disposition can be read at a glance from upstream monitors. These non-actions are as important as actions. They protect credibility from erosion by overreach. Ethical guardrails tighten. If a late analysis were to suggest an intervention with significant externalities, the default answer is no unless international process has already defined the path to yes. The time to argue methods and liability is years, not hours. A world that respects this learns to build governance in quiet seasons. A world that does not will find bad ideas sneaking into rooms on nights when patience is thin. The narrowing window is therefore a mirror that shows whether preparation ran deeper than hardware. There is also an economic window. Insurers set temporary provisions that expire the moment probability drops below a contract line. Exchanges list brief suspensions on derivatives tied to satellite uptime, then remove them once the last crossing hour passes. Launch providers decide whether to slip a mission by a day to avoid clutter in upper air from a predicted meteor storm. Cargo carriers adjust polar routes if scintillation forecasts for navigation signals look unfriendly. None of these moves are dramatic, yet each must be timed precisely. A day early wastes money. An hour late wastes resilience. As the final hours arrive, attention shifts from prediction to readiness for measurement. All sky cameras are checked, bolometers aligned, emission line spectrographs tuned for oxygen, green, and sodium gold. Infrasound arrays confirm calibration. Radar meteor networks raise power for a night of echoes. Aurora watchers set integrations that can catch faint lines if an ion tail brushes the magnetosheath and tickles uncommon species into glow. The window for fear has closed. The window for learning is wide open. There is a human tempo to last minutes. Rooms that hummed all week become quiet. People who have been awake too long are told to sleep because their hands may be needed in the morning. Phones are silenced. A few carry folded pages in their pockets with the essential numbers written by hand, a habit learned from mentors who did not trust screens alone. When the clock strikes, nothing happens everywhere at once. Something happens somewhere first, and then the something travels at the speed of sound, or at the speed of messages, or at the speed of light. After the crossing, the same discipline serves the unwinding. Bulletins shift from forecasts to reports. Plots of observed brightness and rate replace cones of possibility. Photographs of the sky crowd a single public repository so attribution can be tracked and data harvested without delay. Satellite operators return vehicles to nominal attitudes and count anomalies. Airlines file notes on any radio noise along routes. Laboratories request filters, snow, and air from stations that sample the upper air. The window for action has closed, but the window for accountability and learning has opened and will close too if not seized. A narrowing window is only frightening if it is also empty. When it holds checklists, thresholds, schedules, and consent already granted by thoughtful process, it is a frame that sharpens vision rather than a trap that steals time. The sky always narrows windows. The answer is to widen everything else in advance. Trust, practice, clarity. Then, when the last light falls to the horizon and the aperture shrinks to a point, the picture captured in that point will be enough. Practice is a kind of love that a planet can give itself, not the loud kind that shouts from rooftops, but the patient care that repeats motions until they sink beneath thought. Rehearsal begins in small rooms where badges hang on hooks and lists glow on screens. A calendar invites people who do not often sit together. Astronomers bring ephemerides. Air traffic controllers bring routes. Grid operators bring models of lines that cross continents. Language specialists bring the shapes of sentences that travel well between cultures. The first meeting is awkward. The second has rhythm. By the third, everyone knows where to place their laptops so that sockets are close and eyes can see the same clock. The script they follow is a set of simple verbs: see, share, decide, act, record, learn. See means sensors that are always awake. It means telescopes that tile the sky, radars that sweep, spectrometers that listen in the radio where water whispers its presence after sunlight breaks it. See also means people who step outside and look up without instruments. Share means a pipeline that does not kink. Data must cross borders quietly. Hashes must verify integrity. Formats must be plain enough that an engineer in a small country can pass them with code written on a bus. Decide means thresholds posted in advance. Act means checklists that were printed before nerves rose. Record means an archive where timestamps are trusted. Learn means that a report will be written and read by successors who do not yet have names. Exercises bring fiction close to truth. A tabletop drill begins with a card that says a faint object has been identified. The card lists coordinates and a few pixels of motion. Teams respond in sequence. Surveys propose extra exposures. Minor Planet Center star rooms publish a circular. Trajectory crews attach error bars to lines. Spectroscopists request nights while phase angles are kind. Agencies that manage satellites receive provisional contours for possible dust. Aviation gets a quiet message about a radiant that could be noticeable. None of these messages are written for drama. They are written to arrive at the right desk before lunch. In a larger hall, screens surround a model of Earth. Lines arc through space with tiny arrows that pulse when new data arrive. A clock on the wall shows UTC in large digits and local time for 5 cities in smaller ones. There is a sound that means new astrometry, a sound that means updated spectra, a sound that means a model has cleared a quality gate. The room responds as if it were a single muscle. Test bulletins go out in 3 languages, then 10. Social media accounts that belong to agencies wake and post a sentence that begins with a time and ends with a link. The link is to a page that will always use the same layout. People learn where to look on that page. The trust lives partly in that consistency. Rehearsal does not stop at glowing walls. There are field days. Mobile telescopes and trailers drive to places where a predicted shadow will cross a road. Students assemble and practice timing, an occultation with handheld cameras and GPS chips. Amateur radio enthusiasts test a mesh of stations that can carry a signal if networks stumble. Fire departments are invited to a talk that explains why bright sky events are loud, but usually not hot at the ground. and how to steer curious crowds away from windows during a flash. Airport briefings include slides that show what a meteor storm looks like from a cockpit and what to say to tower if one begins during approach. Small things add up to a reflex. Policymakers rehearse too. Treaties acquire teeth when the people who must someday use them have already read them aloud. There are clauses about planetary defense that define who speaks for who pays when a decision has both risks and benefits, and how consent is measured when time is thin. Legal staff script mock press conferences where an official reads a line that makes no promises beyond the next bulletin. Insurance sectors run their own scenarios. They test language in contracts that would cover loss from satellite outages or small impacts. They tune triggers so that premiums do not spike on rumour. Markets value clarity. Clarity is rehearsal made visible. Culture is invited into the room because culture softens the edges of fear. Museums prepare exhibits that show how stones move through space and what past civilizations wrote about them. Artists design posters that name showers and zones of safe watching if a storm lights the night. Schools add modules to science classes that teach phase space as a picture rather than a spell. A child who can draw a corridor of uncertainty on a whiteboard grows into an adult who reads one without dread. That child will know that curiosity is not naive. It is a discipline. Hardware learns from rehearsal. Deep space networks test handovers between dishes at the speed a fast probe would require. Propellant suppliers simulate a surge in demand that would follow a late decision to launch a sentry that had slept in a storage orbit. Ground stations practice uploading new schedules to satellites, in case those satellites must twist to show armoured faces to incoming dust. Laboratories run cold chambers where ice is mixed to match interstellar recipes are warmed and broken under light so that spectra collected by missions have a home to return to. When a night comes that needs these crafts, they will not be new. Memory is part of practice. Reports do not hide mistakes. They list them by name and explain how they were found. A font of public forgiveness is created by honesty long before any emergency. People accept that warnings change because they have been taught that predictions are functions of time. When a map tightens from a region to a coastline to a line on the sea, no one calls it a reversal. They call it progress. The pride in such progress is quiet and does not need a podium. International coordination acquires a ritual. A call is scheduled at a regular hour 3 times a week, even when the sky is calm. Representatives from agencies and observatories join on a secure link. The first 5 minutes are devoted to a round of yes or no questions about readiness. Are radar transmitters healthy? Are optical surveys running nominal cadence? Are data repositories reachable and fast? Then come updates about instruments that will be offline for maintenance. Finally, a short story is told about any new object of interest. The tone is clinical. The words are careful. When a real night arrives, the pattern does not need to be invented. Not every rehearsal is for science staff. Communities practice their own cadence. A city holds a night under dark skies where telescopes line a park and librarians hand out cards that explain how to watch safely. Radio hosts learn a script that fits between songs and is not sensational. Faith leaders receive a page that tells the same facts in different words because comfort travels through many channels. The result is a social fabric that does not tear at the first strange glow. It stretches. It holds. There is room for ambition within caution. An international mission architecture is designed in peacetime that can be assembled quickly from stored parts. One vehicle can sprint for a flyby and send back a torrent of data in days. Another can stay and map the object with patience if geometry allows. A small fleet of chipsats can be released along predicted corridors to taste, dust and field. Their radios speak a simple dialect that any deep station can pass. The parts for such a fleet are built in warm years, not cold ones. Their batteries are topped and tested like smoke alarms. A culture that treats rehearsal as nourishment will fund such measures without drama. Learning curves cannot be rushed, but they can be accelerated. Open code repositories let young scientists run the same models that agencies rely on. Mock datasets are posted with keys that allow students to check their fits against hidden truth. Summer schools bring together people who will someday speak to each other under pressure. They share coffee and syntax and stories about the mentors who taught them to leave notes on whiteboards for the next shift. These meetings are small gifts that pay interest for decades. A planet is more than rock and air. It is a collection of agreements about what matters. Rehearsal writes those agreements in a steady hand. It helps a city know when to glance at the sky and when to check a window latch. It helps a mission know what to pack. It helps a minister choose a sentence that does not wound. It helps a newsroom settle on a headline that informs rather than consumes attention. None of this stops Stone, yet all of it shapes how Stone is met. The next visitor will arrive on a calendar we cannot yet print. It will come in with a number that measures its speed and a curve that holds its path. It will have chemistry inside and dust around it, and motives written by physics. It will not care about fear, or pride, or schedules. People will care. They will look up and then back down to a page that shows what to do. If practice has been honest, the page will be short, the actions clear, the tone steady. There will be mistakes, and the room will own them. There will be beauty, and the room will make space to keep it. Rehearsal for a species is not a spectacle. It is the sound of many small hands turning the same pages at once. It is the quiet of checklists read aloud. It is the soft click of a shutter that captured a moment when a fast light wrote a line across the night, and the softer click of a send button that carried that line to everyone who needed to see it. In that simplicity lives resilience, and from resilience grows a kind of grace that is larger than fear. Outcomes gather in a simple trinity: pass intact, break into a caravan, or burn to nothing in a bloom of ions and light. Each outcome writes a different line in ledgers, kept by telescopes, by laboratories, and by the quieter records that live in habits. Passing intact is the cleanest geometry. A single nucleus curves sunward, brightens, rounds the corner, and climbs out on a mirrored arc. Photometry smooths, torque fades, astrometry tightens into a line that future ephemerides will carry for teaching. Instruments close their shutters in order, and data route to archives whose mirrors sleep on different continents. The science is not finished when the point recedes. Data continue to sharpen models for size, density, activity laws, and thermal skins that flinch under afternoon light. Production rates of gases grow into ratios that are compared with libraries of comets born under other suns or in colder rooms of this one. A single intact flight offers a rare prize, a long continuous light curve that captures the subtle flex of rotation as jets spin and slacken, then ease into quiet on the outbound leg. With an intact passage comes a specific future. Dust released along the arc settles into a broad sheet whose nodes cross planetary lanes at dates that can be computed to the hour. Years later, the sheet may deliver a brief dusting to upper air, a meteor outburst that lasts the time it takes a city to put on a coat. Satellites pass through the remnant veil at a speed that cares little about nostalgia. Those crossings become tests of shields and attitude maneuvers that were drafted on quieter afternoons. In this outcome, risk was a rehearsal, and the memory that persists is the cadence of coordinated measurements that captured a foreign body without forcing a change in ordinary life. Braking is different. A crack becomes a seam becomes a hinge, and a hinge gives way. Pieces separate with offsets measured in meters per second. They brighten and fade as tumbling facets flash and shadow. A chain forms along the original path, each link an irregular shard that breathes for a time and then quiets. The sky writes punctuation marks in quick sequence. Models that predicted clean light curves pivot in minutes to treat a family instead of a single stone. Radar, if geometry allows, paints a handful of shapes separate enough to count, or confirms that the fragments are too small to echo. Cameras shift exposure times to track faster flicker. Occultation teams abandon a single shadow for many, spreading stations thin in hope that one chord will catch a piece. Fragmentation invites laboratories to lean forward. Fireballs that happen to descend over quiet land leave meteorites whose interiors knew darkness for 1 billion winters. Their gases carry noble isotopes that report pressures and temperatures from far nursery years. Oxygen isotope ratios sit on 3 axes, like coordinates in a passport. Micro-CT reveals pores that record sintering and shock. Organics in thin slices tell recipes of hydrogenation, UV browning, and grain surface catalysis. If any fragment survives entry, that stone becomes a second messenger, the first being light that spoke from afar. The fragment answers questions that photons could only raise, and it does so without bending any needle in the clinic of public health. Breaking also writes work for engineers. Fragments dispersed along the track concede one-time meteor activity with rates higher than any shower bred in a bound family. Forecasts then turn into advisories for a night. Star trackers are slewed away from expected radiance, optics are shuttered for a handful of minutes, antenna dishes are parked in attitudes that reduce cross-section. The numbers involved are small compared to storms driven by the sun, but attention is tuned to small. Passing intact asked for choreography of photons, breaking asks for choreography of hardware. Burning is a last extreme. If the orbit dives close enough, the star becomes a furnace that rocks cannot ignore. Ices loft first, then organics char, then silicates sputter into a vapor that swift sunlight strips of electrons. The nucleus shrinks like a snowflake above a candle. Coronagraphs watch a pin of light drag a faint skein across the bright edge of the sun, then shrink to silence. Ion tails detach under pressure, pulses that race outward from the star, grow again, then detach again. Streamers in heliospheric images kink and then soften as the supply fades. What remains is plasma and dust that join the background haze, each bit a seed for nothing but scattered light. Even burning leaves numbers worth keeping. Photometers set to watch the corona capture a small increment in Thomson's scattering, a brightness change not in the million but in a few 10 millions, still legible to instruments that sip at the edge of glare. Spectrographs register forbidden lines from atoms that had slept in ice for ages, and now live minutes as ions in sunlight. Pickup ion monitors near the inner system taste water group species that are not native to the usual wind, then report their rise and fall like a pulse. The star itself does not blink for long. The addition of a small cup of plasma to a river that never sleeps is a story that matters to instruments and to the models they feed, not to the quiet behavior of a grid or a city. All three outcomes contribute to population statistics that matter more than any single night. Size distributions shift when surveys catch the fast and the faint. If the visitor is intact and inert, catalogues adjust the fraction of interstellar bodies that resemble compact stones rather than fragile foams. If it breaks early and often, counts tilt the other way. Either case feeds estimates of how many such travellers can be expected in a decade, as survey coverage approaches permanence. These numbers are insurance math for a planet that will share space with strangers as a routine, not as an exception. They refine detection volumes, they calibrate the rate at which false alarms must be expected and managed, and they validate the cadence of watching systems that were built to serve both science and safety. Culture finds a place in each outcome. Intact passages generate images at dusk, delicate swords that point away from the sun, and parks fill with tripods. A broken chain brings a night of many fireballs that cross at angles too complex for a single gasp to hold. Yet the sound in a city shifts as people talk about the sky at windows and on trains. Burning gives only instruments a feast, while word of it arrives as a note in a feed. A bright dot erased near noon. A clip of polar spacecraft watching a tail tear. None of these moments panic the animal within. They train it, gently, to place spectacle within context. Institutions also adjust. A passing intact event validates data paths that carried predictions without wobble. A breaking event puts checklists to honest work, then records recovery times to sharpen the next rehearsal. A burning event instructs heliophysics centers to fold cometary composition into models of mass loading at the sun's edge. Reports are written out to their last page, where limitations are placed in the same font as achievements. Software is improved in public repositories. Amateur observations are cited with the same care given to major facilities. It is a habit that earns a citizen's continued attention. There is always a thought reserved for the largest tail of possibilities. A fragment large enough to threaten a region is so rare that it lives beyond daily planning, yet it belongs in documents that discuss authority and consent. That discussion is a civic act, not a technical footnote. If a decision ever moves from simulation to action, the language that justifies it must be older than the night on which it is spoken. The three outcomes remind writers to keep that language sharp and modest. Nobility in policy is a practical tool. The simplest end is also the most likely. A visitor passes, a few instruments work harder than usual, a few nights on calendars become pages in papers, and the world proceeds without scars. The dust it left will cross orbital lanes years later and paint a modest hour with quick silver lines. Someone will step outside and say a name, not of fear, but of curiosity, and point. So the triad stands ready for the next occasion. Pass intact and give data for the shelves. Break and share pieces that hands can hold. Burn and feed the sun a thimble while cameras learn. None of these outcomes are a final word. Each is a chapter in a longer book about how small, cold things from beyond meet warmth, and how a planet learns to attach numbers and meaning to that meeting. The absolute worst stays in its small corner, outnumbered by ordinary nights that end with instruments powered down, drives sinking, and people walking home under a sky that has grown quieter by the width of a thought. Afterlight is a quiet arithmetic. Instruments cool, files settle into mirrors, and the sky returns to the durable grammar of stars. What remains is not silence. It is a residue of numbers and habits, a rearranged sense of proportion, and a sharpened respect for small probabilities that coexist with ordinary days. A passing stone from another sun is one event among many, yet it loosens a knot in perspective that tightens during routine. The knot gives way, and a longer view takes its place. Calendars are the first records to change. Agencies pencil recurring time for drills and for shared briefings, with the same emphasis used for storms and fires. Telescopes keep a slot for rapid follow-up that no other proposal can displace. Heliophysics missions reserve a few pages in their command sequences for tail crossings that happen rarely and end quickly. Software repositories add tags that mark stable versions used during tense nights, so that later edits do not erase a path back to what worked. These are small edits in schedules and code, yet they aggregate into muscle memory. A planet grows more fluent by repetition. Language shifts as well. Headlines learn to speak in distances and dates rather than in metaphors. Public bulletins adopt verbs that age gracefully. Verbs like approach, brighten, fragment, recede. The reflex to reach for drama weakens. Calm description earns more attention than exaggerated adjectives. This is not an aesthetic choice. It is a functional one. People build trust when words match outcomes within the tolerance set by physics. In that trust lives the freedom to ask for patience when patience matters, and to request swift action when hours are slim. Children carry another ledger. A few step into classrooms with eyes that remember silver lines at night or a blue sword at dusk. Teachers find it easier to describe orbits after a sky has traced one that was not born here. Diagrams of cones and corridors no longer feel abstract. They feel like the scaffolding behind a memory. A generation that witnessed a visitor, even as a rumour on a screen, learns a relationship to randomness that resists superstition. Small odds do not mean zero. Large energies do not always mean harm. Preparation is not fear, it is stewardship. Laboratories gain objects and constraints. If stones were found, thin sections reveal voids and clasts that tell a pressure history different from local cousins. If no stones reach the ground, spectra alone still refine priors for ices and organics that formed under other lamps. High vacuum chambers repeat thermal cycles and ultraviolet doses until data align with light curves and with lines that once looked like noise. Assumptions shrink, models become modest, and equations that were once confident about water learn to make room for carbon monoxide or for nitrogen frost. Such adjustments do not headline a season. They thicken understanding. Policy grows a spine. Draft treaties move from polite fiction to signed text with clauses that define who notifies whom and when. Liability sentences are rewritten so that responsibility follows action in a way that courts can hold. Export restrictions remember that sensors and code may move faster than old categories allow. A mechanism appears for releasing proprietary data under emergency, with attribution and with care. These moves are not glamorous, but they are the beams that keep a house standing when wind rises. The beams are inspected, then inspected again. Economies learn to flex without breaking. Launch manifests acquire buffers large enough to absorb a short delay, without pulling threads that run through factories and insurance calendars. Satellites practice protective attitudes and return to normal in hours rather than days. Insurance products are tuned so that rumor cannot trigger costly spirals, while real risk can be priced quickly and transparently. Investors discover that depth of preparation, not bravado, predicts resilience. Balance sheets reward planners who favor clean design and clear thresholds. Museums and observatories open doors at twilight when a bright tail sits above the horizon. People stand on lawns wrapped in coats and listen to patient guides. A telescope shows a nucleus as a delicate smear. A polarizing filter makes the coma change texture with a twist. Someone learns that light holds stories about grain size and porosity. Someone else learns that an orbit can be bound or unbound, and that freedom in space wears a precise number called eccentricity. In such moments, the border between knowledge and belonging thins. The sky stops being a ceiling and becomes an address. Numbers also return humility. Error bars never shrink to zero, and stubborn residuals remain in fits that were expected to be clean. The lesson is not defeat, it is scale. Precision is a virtue with limits set by photon counts, by geometry, by the quiet shove of jets that cannot be seen. Accepting those limits is not surrender. It is the ground on which better instruments stand. The next survey builds a wider focal plane. The next spectrograph carves finer slices of color. The next radar transmitter gains a little power. Increment rises on increment until what was a rumor becomes a map in a fraction of a night. Philosophy threads through these ledgers. The worst that could happen is always larger in the mind than on the day. Fear sketches grand fireworks and forgets statistics. Consolation sketches small risks and forgets energy. Wisdom does neither. It holds both in view and binds them with proportionality. A visitor from another sun is a reminder that the local neighborhood is part of a larger city. Traffic is rare, yet not rare enough to ignore. Dignity lies not in immunity, but in conduct. To measure carefully, to speak plainly, to act proportionally, and to learn afterward with kindness for errors is a form of civic grace. Einstein once insisted that the most incomprehensible thing about the universe is that it is comprehensible. That sentence hovers above a room where plots show an arc that was once only a whisper on a sensor. Comprehension here is not total, it is enough. Enough to shrink a corridor to a safe emptiness. Enough to calculate the hour when dust might stripe a sky. Enough to place confidence intervals on claims that carry consequence. Hawking's habit of asking simple questions with large horizons belongs in the same room. Where did it form? How do small forces change fates? What does this visitor say about others that cannot be seen yet? Those questions reach past hazard into meaning. Meaning returns to daily scale when power plants hum without interruption, when aircraft log only unusual glows, when satellites report nothing worse than a handful of recoverable errors, when schools start on time the morning after a meteor storm. Security is not the absence of events, it is the capacity to absorb them. When systems absorb without flinching, people feel the difference even if they cannot name the causes. Confidence flows along unseen pipes. Those pipes are built in peacetime and maintained during lulls by people whose names rarely enter a story. The afterlife belongs to them as much as to telescopes. There is a future in which fast visitors are no longer rare. Surveys will deepen until faint things wake every night on screens. The first dozen will feel startling. The next 100 will instruct. The 1,000th will be a dataset across which statistics sing. In that future, peril does not grow simply because counts rise. Preparation scales, too. The steady cadence of seeing, sharing, deciding, acting, recording and learning will be familiar enough to protect work and family and art from needless interruption. A culture can become good at this without becoming cold. In the end, a small stone lit by another star's light passes a world that has learned to make meaning without making myth. The worst case retains a seat, but it no longer occupies the whole room. It is a reference point held at arm's length while better points are plotted. The better points are curiosity given structure, caution given voice, and humility given tools. Afterlight is not merely the soft glow that follows spectacle, it is the recognition that attention itself is a renewable resource when guided by care. With that resource intact, The next question can be welcomed instead of dreaded, and the next night can be met with instruments ready, language steady, and eyes that still feel wonder. Night keeps a ledger in quiet ink. Waves fold themselves along basalt and salt. Cities inhale and fall to murmurs. On a high ridge, glass cools and dew beads in slow constellations across the dome. Somewhere a late train threads a valley. Its windows a patient necklace that slips through dark like a measured pulse. Sky becomes more sky. In the emptied brightness, a few meteor ghosts finish their errands and fade without fuss. Silence learns new edges. The traveller has already given back to distance. Its curve is now a suggestion at the margin of maps, yet the air remembers. A thin sheen of atoms is still falling through heights, where auroras practice their slow grammar. Instruments remember. A disc spins with a soft click. A plotline thickens by a shade. A note in a log acquires a green check. People remember. In kitchens and bus stops and dim hotel rooms, minds replay a thin white stroke and find in it a sense that the world is larger and kinder than fear allowed. Galaxies hang like winter fruit. Each is an orchard of clocks that do not know one another and keep perfect time anyway. Between them float stones and dust, the smallest ambassadors imaginable, lit by lamps that never read the letters they send. A planet listened for a night and answered with attention. That answer was a kind of music, so quiet it sounded like discipline, so steady it felt like home. It will be played again, not with the same notes, but with the same hands. Dawn will walk up the eastern slope and unfasten the last stars. Coffee will steam, mail will arrive, children will shoulder bags. Someone will check a plot and smile at a line that rests where it should. Someone else will delete a headline draft that leaned too hard on fear and write a better one. The ledger will close with room for more pages. In that room waits the next spark, and the old patience that knows how to look for it. End of script. Sweet dreams.